All right. Hello, everyone. I have returned. So I feel 100% better. My brain works again. My body works again. Everything is good. There is still, it only happened 2 days ago. So due to contagiousness, feel free to come up if you have any questions. But I'll just do COVID rules and stay 6 feet away and all that jazz. But I do feel better. Yeah, there was no possible way I was teaching on Tuesday. My brain was all the blood had left my brain and gone to the rest of my body to help cure it. So, brain was not working. Anywho, thankfully though, recovered quickly. Glad to be back. We're going to Tuesday's class, so obviously you all had a cell. The cell went through things, so a couple things I'm going to do is, and I'm not sure actually if I did this yet. Sometime today, if I haven't done it yet, I'm going to actually post the worked out, so the PowerPoint, I've worked out all the problems that are in here. So I have them worked out in here in kind of a brief kind of way. All the answers to the clicker questions, all that jazz is worked out. This is the last problem we kind of worked on. That one's worked out as well. A few students did request that, hey, are you going to do a screen of it? It sounded that could be useful, and just so everything is available online. So sometime Friday or Monday, I don't know which day, it's going to depend upon timing. Obviously, there's stuff I have to get caught up on because I lost a couple days. I will post some video with me kind of going through it like a normal class, and that will be available, going through the slides that we went through on Tuesday. So those will be there. The good news is that the stuff that was covered on Tuesday is going to kind of show up again today in a different form. So we're going to see the same stuff. We're going to get to kind of practice it some within a new context and some new things. So I'm going to go over that in just a bit. Before I do so, it is on track for me to have those 3 response grades posted by this Friday. So those grades, the graders did confirm that they're all done. They're just inputting the grades. And so by tomorrow, what I will do is I will then look through those. I will look at the ones that I've kind of graded. And then kind of evaluate how to post those and what's going to happen there. I will warn you all, generally, I do not do curves for the free response for the reason that there's partial credit. And so the partial credit basically then is at the end of the day, there's partial credit and there was a choice. So if there was something I kind of didn't cover well, you could have picked kind of the other questions. So that's why I don't generally give curves in. The purpose of curves is not to get the grades to a certain percentage. I do not curve the grades to get to a certain percentage. By the end of this class, my goal is not that X number of people have A's, X number of people have B's, X number of people have C's. The goal at the end of this class is that I have given you all the resources available. Basically, the university / the state says, hey, here are the things that people should know by the end of Physics 2. Then my goal is to then give you the resources, the training, and then assessments to say that by the end, do you know said things. Depending on how much you know, depends kind of then on your grade of the class, also with effort. Those 2 things for me are both valuable. So to that end, I want, if every single person here got an A, that would be fine by me assuming that everyone earned an A because they actually understood the content. I need those 2 things. It's a long story short, I need the grades to align with your understanding. So why do I say that? The only reason I give curves is if I have kind of failed you in some way. If I have not prepared you all, so in the case of multiple choice, there were the 2 Gauss's law problems. I had the data showing a vast majority of students missed those, therefore I did not prepare you well for those. If I look kind of across all the free response, if those are low, it's kind of a big claim to say I didn't prepare you well for all 3 free responses. That's kind of a large claim. And I give that in point to problems that are similar, yada, yada, yada. If I think of this a short syllabus. Yeah, is it not streaming?
No, not.
Weird. It says it's streaming.
No, it's streaming.
Okay, great. Great. Is it under lecture or did I click the wrong button? Great. Okay, cool. Thank you. Do let me know if this number doesn't seem to work because that saves you a lot of headache and extra time. All right, so anyway, just giving you all a heads up that there might not be a curve in the free response, and that's why. Yeah.
Will the free response average with or like go on top of the one?
Yeah, it's a good question. So I heard some concerns that so the free response, the multiple choice is 60%, the free response is 40%. I heard some concerns within web courses. I had used the old style previously. It was 80%, 20%. You're like, why did you change it? It's because it used to be pick one free response out of two. And here I did pick 2 out of 3, so I doubled the number of free responses. So that was kind of an antiquated thing. In the syllabus, it didn't actually outline how the distribution was, so it wasn't like I made a change that went against the syllabus. And on the test itself, it did say 60% was multiple choice and 40% was free response. But I just didn't communicate that well beforehand. So to that end, you all have 2 categories in the gradebook. One is multiple choice, one is free response. And then there's one that's called the total. The only reason there's 3 categories is to give you all a higher resolution in terms of how you did on each part. So I let you know how you did on multiple choice, I let you know how you did in the free response, and then the total just shows you them combined without you having to do the math. At the end of the day, I actually only count the multiple choice and the free response in the gradebook. The total is not actually counted, and the reason it's not counted is to not double count the grades. But I put them all there just to give you the resolution to see kind of where the points are distributed.
I was just going to ask because it looks like all 3.
Okay, I'll double check that. Yeah, thank you for letting me know. I'll double check that. And what I'll end up doing as well is, again, that survey also will be included in all those things as well. Okay, so great. That's that. That'll be posted tomorrow. I'll send out all the details with all the things when that's done. Now the next thing I'm going to do is I'm just going to point out, I told you all that there's AI assignments. This has been kind of a placeholder for a while. Me and someone else are collaborating to make these. What I told you at the beginning of the semester is that AI is a new tool, new, quote unquote, last few years, 5 years, so. And the reality is, if you do not know how to utilize it well, you will be less marketable as an employee. If we think back to 10 to 15 to 20 years ago, maybe longer actually, 30 years, whatever. When the internet started to kind of ramp up, it was the same thing. If you were not proficient in using the internet, you became less marketable. Before that, if you were less able to use computers, you were less. This has always been a thing. When a new technology comes out, you can call it maybe disruptive technology, not disruptive in a negative sense, but disruptive as in it causes sweeping changes. Those that know how to use it are more marketable and able to be more efficient and able to adapt to a changing world. Those that do not end up still being able to get the job done, but it takes them more time. It is harder for them to get a job, etc., etc. So to that end, one of the things I want to train you all is how to use it to learn. Because you all are going to hopefully be lifelong learners, which sounds like a cliche statement. But if you're building things and making things, or trying to solve problems that someone else hasn't solved, by nature, that means you have to learn new things. How to use AI to learn new things is a skill we can practice in this class. And so to that end, there's going to basically be 2 assignments that we currently have planned. The first, and they're both just going to be if you do it, you get the points. Really straightforward. But the first one is using AI in an effective way to learn how to solve a problem. Not just copy and pasting the problem, spitting it out and saying, yep, great, I've learned it, because that's not how learning works. How to use it, how to converse with AI effectively, how to have a back and forth conversation with it. That's one thing. Then the next will be, and this assignment will be later, how to use AI to generate similar problems for similar practice and things like that. So those will be kind of the 2 things we have in mind. One of the documents we're working on, and I'll have this completed ideally by the end of the week, and we'll have stuff on Monday, is we kind of have this handout we're working on, which basically is first going to say there's various levels of using it. So I can chat about this now. These 5 levels, there's something called Bloom's taxonomy, which anyone that's done any education stuff might have heard about. It's the 5, there's various levels of learning. The first one is kind of passive, which means you just get information. It's like me telling you that my car is red. Great, you know my car is red, but it's just facts. The next one is kind of a surface level, which means you're learning a little bit more, you're engaged a little bit, not as much, or more than that. The third one is kind of a collaborative, you're actively engaged with it, and then kind of the fourth and fifth one is that you're really taking a leading role in the thing. You are designing something, you are creating something. You're not so much learning so much as developing and making new things. We want to exist at level 3 in this class, as far as when you're engaging with your content. It is useful sometimes just to have facts, but the reality is, you probably learned this in the physics class by now, it's not about the facts, it's about do you know how to apply it, the process. And so your class is moving forward in a STEM degree, you are very much at the 3rd level. If you're in a history, depending on your thing, if you're taking a GEP history class, you're probably more at the 1st level. If you're a history major, you'd still be active in a different way, whatever. So, I use the analogy of a car. I'll chat about this more on Tuesday. But then down here, then we have some guides for how to use it in an engaging way and basically giving you some prompts. So the first thing I kind of put here is don't just copy and paste and hit enter. That is that passive level. You're just seeing what it did. If you leave it there, you're not really doing much. But what you can do is you can copy and paste the problem and then ask it, hey, use guided inquiry. Guided inquiry is where it asks you questions and you answer questions to it. Ask it to act like a tutor who's helping. You can just tell it who you are and what you want it to be, and it will generally fulfill that role better. I want to solve this problem by this process. Is this correct? I tried solving it this way, got a blank answer, helped me identify. This one I was shocked with. I just tested it this morning. Attached is a picture of my work. Where did I go wrong in the process? So I use ChatGPT, not because it's better, but because I just was able to get a paid version of it through some things. And I just asked it a quick question about circuit analysis. And so a student, not from our class, from another class, had sent me a problem, and this is my worked out thing. And it's kind of like, I didn't even put the problem, and it's my handout work. And I just said, hey, can you read this? Because I was curious how good it was at reading handwritten work. And it says, it then provided, this is a network this is resistors getting combined together. These are in series, these are in parallel. Here's the math you did, here's the numbers you generated. I was very surprised at its ability to read handwritten work. These strategies I'm telling you, the reason I was able to come up with these strategies, I'm just trying to teach you how to engage with AI in the way that I engage with people that come to my office hours. When I engage people in office hours and they ask me a question, I don't just give them the full worked out solution. What do? I ask questions. I say, hey, what did you do? Show me your work. And then I might point out where there was a mistake, or I might ask them a follow-up question. So all I'm trying to do is to train you all to basically have it act like me or any other tutor. Anyway, the next one, make sure your question's clear. Again, I'll send this out to you all later. I just wanted to give you a kind of preview of what it's going to be. Make sure you ask for follow-up questions. Why did you do this? What if this was changed instead of this? What if it asked for this instead of this? How did you know to use this equation? What if I used blank method to solve this problem instead? All these prompts are coming from questions that students have asked me, or I ask students to help them learn. And then the last thing is very, very, very important. AI is pretty darn good at solving problems at this point. However, it makes as many mistakes as probably I do. And I don't make 0 mistakes. I make mistakes. So to that end, one of the best things that's really important, honestly, when you are in this learning stage, is that you know what the right answer is. So when it spits out an answer, you can check if what it spit out is the same. Now, when I give it a problem to actually, I haven't checked my own problems. It's always good to double check your work, and this serves as an extra person to check my work. I don't give it the right answer. I say, hey, here's the problem. I want you to check my work. I've already done the problem and solved it myself. I know what I think the right answer is. If it gets a different answer, then I try to figure out why. But I have an answer that I know is kind of correct. So I don't give it that right answer, though, because that's going to kind of bias it. I let it just kind of work through it, just like someone else would. And I find that results in generally a more thorough analysis. Whereas if you give it the answer, it might act like it's solving the problem, but it didn't actually solve it. Makes it work a little harder, just like I have you all do when I don't give you the something. So, anywho, but I put that as the last step, is you can then tell it the right answer. But you can also ask it for websites or videos. So, anyway, I'll send this all out. But yeah, the more details of this will come out Tuesday. But I wanted to give you a preview that this is going to be a thing that will exist. Because it's important and it's useful. And currently, I think a lot of people use AI in here's the problem, hit enter, there's a solution, look it over, never actually touch a pencil, never actually write anything down, and then say, yep, I understand it, and that's not ideal. This has always been true. People back in the day, Chegg, everyone knows you all are kind of in that hybrid zone of AI and things like that. How do a lot of people solve problems? You put the problem, you Google it, you find it on Chegg, you look at the worked out solution, you say, that makes sense, and it's not good. Like, that doesn't result in learning. That results in, I know how to solve this exact problem. If one is slightly different, I have no idea what to do. And funny enough, this is a problem that exists at the graduate level too. This is actually a conversation we had in our department about things. Anyway, great. So, preview. Awesome. Okay, so last class, normally I'd say me, but it wasn't me, taught you all that magnetic fields exist. And what's important about magnetic fields is they cause forces on charges, but the charges have to be doing something. Specifically, and I'm trying to find the exact slide on it, they have to be moving. And this is a very weird thing. This force is very weird because, one, your charges be moving. There's not really any other force that you all have experienced where something has to be moving. Maybe you talk about air resistance, maybe. But your thing has to be moving, and even weirder than that, the force, every force you all have ever seen is generally in the direction of the field. So the magnetic force or the electric force is in the direction or opposite direction. It was like fairly intuitive. Gravitational force, same thing. This one is 90 degrees to it, which is very weird. Meaning, if an object is moving to the right, and I have a magnetic field into the page, so I'm going to give you all an example here, and there were some other examples, we're going to get some practice today. There was actually quite a few of these. So if I have a positive charge moving to the right, and there's a magnetic field going into the page, the force is not going to be to the right. The force is not going to be into the page. The force is going to be, in this case, up, which is weird. It could be if this is a negative charge. But this is a systematic way. And the way I generated this force wasn't made up. I just did something in my head. I did the right-hand rule. The right-hand rule, the swinging door method, I'm going to go over very quickly. Again, I'm not going to spend too much time on this. Every right-hand rule starts with you making like an L, I guess, with your hand. Very important that your thumb is at a 90-degree angle to your hand. Every problem starts with you making this like L. And I took a picture of this because drawing a picture of a hand is very hard with 3 dimensions. So this is my solution. So you take your hand. You put your fingers in the direction a positive charge is moving. So this is from positive charges. Now, negative charges we'll get to later. Let me get through it. Yeah. So we'll apply this and then I'll answer any questions. I'll say you got your hand. And here I have pictures showing velocity in a magnetic field example to help us kind of walk through this. So you take your hand and you point your fingers in the direction it's moving. So in this case, the example I gave here, the charge is moving to the left. So I point my fingers to the left. My fingers need to always be pointed that way. Do not do anything. If I move those fingers, they're not pointed towards it, I've done something wrong. So they need to be pointed that way. Now the next key, I call this the swinging door method. That's kind of the way I visualize this. Imagine your fingers are like a door. And doors can swing. They can swing on a hinge. Your knuckles are kind of like the hinge. Your goal is to make it so I can swing this door towards B. I need to be able to swing my fingers towards B. So let me give you some examples where that's not possible. This current setup, it's not possible. If you all look at the picture here, the way my hand is currently aligned, I cannot swing my fingers towards B. But do it yourself, and you can't swing your fingers downwards. B is downwards. I cannot swing my fingers downwards when my hand is in this orientation. Hopefully everyone's cool with my fingers can only swing in like this way. So what do? I rotate my arm. You can twist your arm. And by twisting your arm, what I can do is I can twist it so that it can swing towards B. Again, think about that I want to take this V, think of it like a door. I want to swing this. I want to swing that V towards B. How do I make it so my fingers can swing towards B? Look at the next picture. I rotated my arm, and now my fingers can swing towards B. You need to visualize basically taking this vector and swinging it towards it. We call this a curl. It's a cross product. This is kind of what happened to do a cross product. So by making it in this orientation, my V is still the right way, but I can swing it towards B. What's the end result? My thumb points in the direction of the force. That's the whole point of this. That's the reason we go through this process. And this force is perpendicular to the direction I'm moving. Now, you might have seen there's other ways to do this. There's like this, I don't know what to call it, where you kind of put your fingers at right angles to each other. The problem with this method is what if my thing's not at perfectly 90 degrees to each other? So let me quickly show you all an example. Again, I'm not going to work through them all today. There is these examples that were given in last class. You may or may not work through them. I have the answers here. I'll post the video. If we look at answer D, part D, this is the one where I'll show you. It's kind of really tricky to do with this method. But if you put your fingers towards B, so again, you take your hand, make that L, and point it towards B, I need to swing the V so that it swings all the way to B. I need to make my hand so that I can swing this V so that it swings all the way like a door to B. How do I orient my hand so that I can swing it all the way to B? You have to visualize this kind of swinging motion and then make your hand do it. So I take my hand, I put it here. I can't swing my fingers backwards. That's not going to work. Can't do it. And I can't even swing them this way. It's not possible to swing them far enough. So that's kind of your check. If I do it this way, I still can't swing them. If I do it this way, I can swing that velocity vector over to B. Now, the direction of my thumb is into the page, and this then touches on the other point. Negative charges always do the opposite. Negative charges always do the opposite. So when I do the swinging, I get a force into the page. Which way is the actual force? Out of the page. Okay? This is something you have to practice. In the problem set, there's 8 different versions of this. There is so many versions of this to help you all practice this, because the reason we use our right hand is because it's just easier to kind of do that. You can, as you do it enough, you can kind of sort of do it with your head, but I still do it with my hand. It's a nice physical way of representing it and seeing it and all that good stuff. Okay, we're going to get some more practice with it today. The other thing that was covered in class is that because this force is perpendicular, always perpendicular, the question I asked was, hey, I got a charge going through a field. What's the path it's going to take? And what we found is it makes a circle. Why does it make a circle? Because on the bottom, it gets pushed up. On the side, it gets pushed to the left. On the top, it gets pushed down. As it's going through this motion, it gets pulled towards the center. And so it makes a circle. And what's interesting about this means it doesn't speed it up, it doesn't slow it down, it just changes its direction. Magnetic fields don't do work. They don't speed up charges. They do not slow down charges. They only change their direction. Magnetic fields can only change the direction a charge moves. This is very practical. Way back in the day, they had cathode ray TVs. How did cathode ray TVs work? They literally shot electrons at a phosphorus screen. And how did they move them? Magnetic fields. Super, super practical. That's one way they're used. Another one is in magnetic field accelerators. Another one was Earth's magnetic field. Actually, this is why the northern lights happen. They only happen at the north and the south. Why? Charges hit the Earth's magnetic field and they spiral and they follow the path of that field and then they hit the top of the atmosphere, and that's why the northern lights are only at the top of the atmosphere. So, used in a lot of different applications, mass spectrometers, all that fun things. Yes, sir.
Where do the fields come from?
The Earth's magnetic field is theorized to come from a spinning iron core, specifically moving charges. So that's actually something we're going to learn next week, is that what experiences forces due to a magnetic field? Moving charges. So what makes magnetic fields? Moving charges. And so in the center of the earth, we have a bunch of charges spinning. Yeah, it's a good question. All right, so more things. I'll make a video. It'll be great. So let's move on to the new stuff that I hope to get through today. Force on a current carrying wire. So great. Last class we quote unquote talked about, hey, moving charges experiencing force. What do we call a whole bunch of moving charges? Current. So therefore, if one charge experiences a force, a whole bunch of moving charges experience a force. And this is more commonly the application of this. So it's a really simple argument. If one charge experiences it, so do a bunch of them. Alright, the derivation actually is pretty simple. We're just going to do some it's a little hand-wavy, but it does the job. So this is the equation for the force in a moving charge. Q, V, cross B. This cross product is what's giving us that 90-degree thing. You all in Calc 3 should be learning about cross products and all that good stuff. V is defined as dx dt. That is the definition of velocity. So, the force on a single moving charge is Q times dx dt cross B. Cool. All right. So therefore, just rearranging things, the force that a single charge experiences, and this is where we're going to do something. What if we make this Q really small? How do we make it really small? We do like df. If I want a really small thing, and then we make this dq, we just make it really small. That gives us a really small piece of the force. Why is this going to be important? We're going to see in just a second. The derivation is almost done already. Rearrange the terms. We get dq over dt times dx. And we're basically done. dq dt is something we've seen before. It's current. Boom, we derived it. This is the equation for the force in a moving charge. We're just going to write something slightly different. Remember, x can be written as a ton of different variables. In this case, x is along the wire. We often describe that as dl. Instead of dx, we'll put dl, where dl is the direction that the wire is going. Same direction. We've done the opposite a lot of times in this class. We changed dl to dx. We can do the other thing. So, boom, there's the equation. If I want the tiny bit of force on a tiny piece of the wire, it's I dl cross B. I do not need you to know how to do cross products in this class. I do not need you to set up, if you're like, what does it mean by doing cross products? I do need you to know that cross product is equal to the sum of the multiplication of the terms times sine of angle. I need you to know what's written here. I do not need you to know how to do this. You all in Calc 3 might have started to see this. Yeah, so this whole doing the cross product thing and you do the cross, I do not need you to do that in this class. I do need you to know this right here, where theta is the angle between L and B. It's the angle between them. That's going to be very, very important when we solve these problems. Now, notice that I define this in terms of df. So if we want to get the total f, what are we going to have to do? We're going to have to integrate it. We're going to do some problems with integration. They are not bad. They are using the same process you all used for Coulomb's law. Draw a picture, substitute the terms, x and y component. It's the same process. At the end of the day, that process I'm teaching you of building an integral is just the process for building an infinite sum of, it applies to almost any integral you're going to learn in future classes. If I can figure it out for a small piece, an integral will give you for the whole piece. This is a very, very useful skill. You all have learned a lot of how to use algebra in the real world. I'm trying to convey how to use calculus in the real world. Your calculus class has just taught you how to do the math. Just like your all's grade school, you learned how to do algebra. And then you got to physics 1 and you had to apply it to real world scenarios. I'm now building on that and trying to teach you all how to use calculus in real world scenarios. That's why I keep harping on this. It's something you all need to know how to do. Otherwise, why did you learn calculus? All right, if the wire is straight, df just becomes f, dl becomes l because I is a constant, the angle is constant. So that's the simple case.
B is the magnetic field itself.
B is the magnetic field, yes. And just a quick background on that. I looked up the history of why B was chosen for magnetic field. It's not quite clear. There's some disagreements in it. One of the theories I've heard, though, is that when the person who defined this, he just made like a bullet point list of like one would be called A, one would be called B, then C, then D, then E, then F, and D just happened to be magnetic field. So he just listed them A, B, C, D, E, F for a bunch of things. A was the vector potential for the magnetic field. Don't worry about that. Whatever. So B, it's what we chose. It's what we use. All right. So this is going to be a good practice for the same rule that we just used for a moving positive charge applies to this. It's the exact same technique. The only thing you will need to remember is that current is the direction a positive charge is moving. So these are a bunch of positive charges moving to the right in a field that points into the page. Do the right-hand rule. Which way is the force on this straight wire? It's going to be the same direction everywhere on the wire. See if y'all can figure it out. Do that technique we did a quick review on at the beginning of class. Point your fingers in the direction of it, of the moving positive charge, and make it so they can swing towards B. Make it so you can take that moving charge and swing it so it now points in the direction of B, and your thumb gives you the force. All right, give y'all 20 more seconds. All right, 5, 4, 3, 2, 1. All right, a key when you're solving these, you need to line up your hand to the, in my case, it's the board, but if that's your screen, when you're doing a test, you line it up to the paper. Your reference needs to stay the same. So in my case, I'm going to use the reference of the screen up here. So I take my fingers and I point them in the direction that my charge is moving. My positive charge is moving, so my fingers point to the left. Great. I need to make my fingers. I want to take this current and I want to swing it towards B. I want to go swing that vector towards B. How do I make? I then need to rotate my hand so I can make that happen. If I have it this way, with my thumb pointed into the board, it is not possible to swing my fingers inwards. I can't. If I swing my fingers inward, I'm twisting my... Your knuckles are the hinge. That's the only part that can swing. So I point it here. The only way I can get it to swing is I put my knuckles facing outwards, so then it can swing inwards. And which way is my force? Upwards. Think of your hand like a door. That is the most useful way that at least I can think of it. That's how I visualize this. If I do this in my head, I physically think of swinging it. Swing towards B. Oh, a notation here that maybe this got mentioned on Monday or Tuesday. This X means into the page. X means into. Dot means out. There is a nice trick to this, and it's in the slides. The trick to remembering this is think of like a bow and arrow. Think of like a bow and arrow, like the kind that you shoot at a target. The arrow has feathers on the back and a tip on the front. If you saw an arrow getting shot into the board, you'd see the back of the arrow. The feathers look like a cross. If you saw an arrow coming out of the board, getting shot at you, it would look like the tip of the arrow, which is a dot. This is how I remember this. Think of a physical arrow, and that's the way into it. You see the back of it, out of it, you see the tip.
So could you do the right hand rule and go down?
Yeah, so if you try to do the right hand roll any other direction, so if you try to do it this way, my fingers need to swing this into the page. It's very hard to draw this. These B fields are kind of pointed into the page. I can't draw an arrow into the page. That's where we draw these X's. But I need to make this eye swing inwards. My arm here is pointed into it. I need to make this arm swing inwards. Yeah. Great question. Do you have to use your right hand? Try it with your left hand. See what happens. Try it real quick. Do the same exact process with your left hand. This is a great exercise to show you all why it's called the right hand rule. Point it here. Make it swing into the board. Which way does your thumb point? It's the wrong direction. I love that you asked that because this is a very important thing. Most of you all are right-handed. Not everyone. Most of you are right-handed. On a test, when you're solving this problem, you're going to be holding your pencil. It's very tempting to use your other hand to solve these problems. Do not do that. Unless you know that the answer is backwards. Your left hand is for a negative charge. Your right hand is for a positive charge.
I got confused because it was pointing up, but at the same time I was going out of the page. So what is the difference between the two? Like, what would be an example of the page?
What would be an example? So this one's up, so it's, so into the page is always what it sounds like. Imagine literally going into the physical page. Yeah. So if you took this and you put it flat on your finger, it's still going to be into the page. So this is an important thing. When I give you a question, this is the directions. Up, down, left, right, into the page is into the page, out of the page is out of the page. I will always use this wording. Up will always mean to the top of your paper. Down will always mean to the bottom of your paper. What would be an example where the force is up? Or in this case, into the page. If my magnetic field was pointed down. If my magnetic field was pointed down, then I would swing this way and it would go into the page.
What if, you said negative charge or left?
Yeah. Negative charge will give you the exact opposite, which subsequently is the rule for negative charges. All right. You have to practice the right-hand rule. There is no getting around this. How do you learn to use a hammer or a screwdriver? By physically holding a hammer and a screwdriver. This is literally a physical thing you're doing with your hands. I cannot do this for you. No matter how many times you see me do it, until you do this a bunch of times, it will not make sense. I can promise you that.
I mean, I just assumed B was into the page. That's how they were swinging.
B is into the page.
So, how is it not into the page? We're swinging towards it.
We are swinging it. Your thumb tells you the direction of the force. Your thumb tells you the direction of the force. The key when you're doing right-hand rule, the force is always perpendicular to the direction you're going. All right.
Thank you.
Yep. So, all right, let's make this more interesting. This is for a straight wire where the current's always going in the same direction. What if my wire is not always going in the same direction? I have a curved wire here. Curved wires exist. Not a crazy idea. A curved wire, what is the direction of the force on just this half loop of wire? I have a magnetic field pointed into the page, and I have a half loop, specifically the top of the half loop, and it's going clockwise. Hint, find the force on a small piece on the left side. I don't care where, look, pick a little piece right here. Which way is the current moving on this little purple line I drew? Where is the current moving on a purple line on the exact opposite side? Use symmetry. Find the force on each of these pieces and see if anything convenient happens. That's my hint to you all. Try it out. You have to do this more than once now. You need to find the force on at least 2 pieces of the wire to get the answer. And then apply symmetry. I highly recommend drawing these things on a piece of paper in front of you. It will help you a lot. Draw the direction of I on the top left and the B. Draw the direction of I and B on the top right. I'm going to give you time to do that. Draw it on your paper and make your hand match. Draw the direction of current on this little piece here. Let's call this piece 1. I'm going to pick a different color so it's easier to see. What color is the brightest? Draw the direction of those currents. I didn't draw them for you. I want you to think about that. What is the direction of those lines? You got 2 options. One's right. And this would be a very easy multiple choice question to put on the test, or a variation of this. This is kind of the level you all should be able to do, just like be prepared. All right, give you all 20 more seconds. I think we're getting near the end. All right, in 5, 4, 3, 2, 1. Yeah. You sometimes got to do some convoluted kind of motions. It's always fun on test 2 to watch everyone do a bunch of hand motions during the test. It's all part of the fun. But the fun fact is when you look around at people, so many people are going to be doing so many different hand motions, it's not useful at all. You have no idea what problem they're working on. It's not interpretable at all. All right. So I'm going to call this first little strip. DL1. In what direction? It's a vector. What's the direction of it? Up and to the right. Why? That's the tangent line to this circle. Why is it up to the right? Because the current is going clockwise. So you got to take, one of those 2 directions. DL2 is going to go down and to the right. So the first one went up to the right. This one's going to go down to the right. Currently, this does not give us any answers. This just helps us start the process. DL1, I want to find the force. I put my hand in the direction of DL1. I'm rotating because I haven't picked which way it's going to be oriented yet. I need to swing this arrow. My magnetic field points into the page. My leg is pointed this way. I need to swing it. How do I do that? I put my hand there, and I can swing my fingers into the page when they're in this orientation. Which way is my thumb point? It does not point up. It does not point down. It does not point left. It points up to the left. My force points up to the left. So the direction of the force on that length of wire. Well, looks like it's green forever. Not anymore. We're stuck. Such is technology. All right, great. The force. And what are we going to call this? We're not going to call it F. We're going to call it DF1. Get in the idea that DF is just a tiny piece of F. What is F? F is the force of the entire thing. DF is a tiny piece of that. Repeat the process for DL2. Which way does DL2 point? Down to the right. Put your hand down to the right. Swing it towards B. Make your hand so it can swing towards B. Which way does that force point? Up and to the right. Through the power of symmetry, I have an arrow pointed up to the right. I have an arrow pointed up to the left. Again, it's split wheel. Up to the left, up to the right. Hopefully you all have done enough problems now to realize that when you kind of add these together, the x components will cancel. One's to the right, one's to the left. They are equal and they're up and left in the symmetry of the problem. Symmetry is always a beautiful thing. And the end result is if I added these two vectors together, I get that my f here is going to be up. Now, but you're like, but there's so many other pieces of the wire. Symmetry. Pick any. I just picked a random spot in this work. It's going to work anywhere else in this, and they're all going to contribute such that my force is pointed up. All the x and y components will cancel.
Can you show doing the right hand rule again?
Yeah. So we put our fingers in the direction. We do DL1. We put our fingers in the direction of DL, and then just swing my fingers to point towards B. These problems, the next couple weeks. It's a lot of three-dimensional kind of visualization here. You have to physically imagine an arrow pointed into this so that you can imagine swinging it towards it. You're going to get a lot of practice with this. Being able to visualize things in 3 dimensions is a skill every single one of you needs to be able to work in. Even computer science majors, yours is actually worse. You are going to work in matrix. You are going to work with matrices. And you might even have more than 3 dimensions, which gets complicated in how you visualize that. But a matrix is just, depending on how many columns and how many rows, is how many dimensions you have. Everyone else, obviously, mechanical engineers, aerospace engineers, you're working with the 3D world. You need to be able to visualize in 3 dimensions.
In the beginning, you were rotating your hands because you weren't sure where you were pointing it. So,
you need to be able to swing DL to point in the direction of B.
oh, okay.
Yeah, that's the idea. Swing DL so it points in the direction of B.
See, like the arrow, I thought was supposed to match with our thumb, but it seems like we're supposed to stick an arrow.
The fingers match in the direction of current, and then you want to swing those towards B, and your thumb gives you the force. Your thumb gives you the force.
I mean, it seems like the thumb's always pointing up.
Oh, it won't be. There'll be some case. This one doesn't point up. It points up to left. And in fact, if you're all the way over here, DL points this way, my force points this way. I'm going to just pick a bunch of different spots on here and give you the force.
Right.
The force always kind of points radially outward in this picture. You cannot just memorize these problems. Why? I can very easily make this field all sorts of different directions. Make the field to the right, make the field up, make the field to the left, make the field like... Yeah, either one, yeah.
How did you do the second one without breaking your dress?
The second one?
Yeah.
Yeah. It's a little inconvenient, but... Yeah, great question. If it was a complete circle of wire, yes, the force would be 0. And that is actually a rule. There is a rule that if you have an entire loop of wire in a magnetic field, the net force on it is 0. Why? If the net force was non-zero, it would make it move. It would increase its velocity. You cannot increase the velocity of a system by applying a magnetic field. You can do, not of the entire system. You can increase the velocity of tiny pieces of it. We're going to see that in a little bit. But the net effect all cancels out.
What would be like if the magnetic field was going out?
Yeah, if the magnetic field was going out, the answer would be exactly the opposite. The force would be downwards. That is a great question. Basically, if you have the answer for one field, if you flip the field, the force will be exactly opposite. It's exactly what hopefully you'd want it to be. All right. There is examples of these again in the problem set to help you practice. This is actually one of them, I believe. All right, so don't know where the picture went. Luckily, it's from the problem set, so let me just pull up the problem set for you all. So I have updated the problem set, and in fact, I've updated it for this week and next week. Again, I'm constantly like 1 week ahead of y'all. So, problem number 11. Find the force on this wire. So this is the problem we're going to solve. I'm going to copy this picture real quick. I have had to make all these images, so not a huge deal, but this is part of what, if you're like, what takes so long on his end to make all these diagrams? Very likely in these problems, I often give you a picture if I have a complex geometry, because describing it in words is awful. So here's a complex geometry. All right, find the net force on the wire below. If the current equals 5 amps and the magnetic field equals 0.15 Tesla. Now, the magnetic field here is pointing to the right. My wire is doing it's doing 4 things. Yeah, it is making a shark fin, which is useful. Actually, that's a useful way. It does look like a shark fin, so we're going to look at it. On this left side, which is kind of like the flat water. This is helpful for anyone online or just being able to describe it. We're going to break this into 4 pieces. Why? If I want the total force on this wire, I need to find the force on each piece. You got to break it into pieces. So we got piece 1, which is kind of like the flat water on the left side. We got the vertical portion here, which is like the left side of the shark fin. We have this downward part, right side of the shark fin, and then we got this flat part here. All right, I want you all to find the direction of the force on each of these parts. Before we even solve this problem, find the direction of the force on each of these parts, and then we'll actually do the math to combine them.
We need the length of the water.
Huh?
We need the length of the part plate.
What a great question. If you need something, it would be given in the problem.
Are the 2 flat plates of the wire infinite or like? Would they cancel each other?
Yeah, it's a great question. Are they infinite? If you want them to be, they can be. If you want them to be short, they can be short. When it came to the right-hand rule, we didn't actually define the length of the wire or anything like that. All right, some of you kind of, I think, have stumbled upon this, so something I didn't explicitly say would have come out in last PowerPoints. What happens if they line up with each other? What happens if my current, my moving charges are parallel to my magnetic field? Then I can't swing my door at all. So what's the direction of my force? There is no force. If the direction of motion is parallel to the magnetic field, nothing happens. Nothing happens. A cross product is multiplying the parts of vectors that are perpendicular to each other. That's what a cross product does. A dot product multiplies the parts of vectors that are parallel. A cross product multiplies the parts that are perpendicular. If they are completely parallel, no part is perpendicular. So, we quickly find that this force is 0. That's just a rule, but we're going to see it mathematically. I'll prove it to you mathematically. The force on 4 is also 0. Now, the other ones are more interesting. Make sure you draw arrows. Make sure you know the direction of current. You can't do this if you don't know the direction of current. All right, for branch 2, I point my fingers up, and I want to swing this towards B. Yeah.
If there were no arrows, are we to assume it goes clockwise?
That's a good question. There is secretly little arrows here. When I zoomed out the picture, it was a little harder to see, but the original picture had a much nicer. Yeah. The original picture did have the arrows. They just kind of shrunk when I copied and pasted it. Yeah, I will define the direct. I have to define the direction of current for you all. All right. So I put my fingers up, and I need to swing this in the direction of B. So how do I do that? I point them up, and I rotate my hand so I can swing it to the right. My force is into the page. My force here is into the page. Why? because that's the direction my thumb points.
Why isn't it the other way around?
So I'm going to swing this towards B. So if I swing it, your hand's the wrong way. You can't swing your hand backwards. Yeah, so let's go through. How many ways can you swing your hand? If I have it this way, can I swing my hand towards B? No. If I have it this way, can I swing my hand towards B? No. Your fingers should not be able to bend backwards. Now, I have very flexible fingers. My fingers can bend really nicely backwards. It was a great thing in grade school in Mercy I was very good at. My fingers can bend backwards. But most of your hands can't bend backwards very far. Mind you. No, I don't know why. It's a gift. Yeah, it's good for me. It worked out great in elementary school. Now, in this case, which way can it? Oh, look, this is nice and not hurting anyone's hands. I can swing it towards B. All right. Now, we're going to do 3. I need to swing this one towards B. I put my fingers down to the right. Again, this is always going to be a little awkward, especially when I have to hold my hand way up here. I need to swing them towards B. If you need to, draw B closer to it. That's the direction of B. How do I swing it towards B? I swing it upwards. My fingers point out of the page. My force points out of the page. Why does this matter? I have a vector in and a vector out. They're going to subtract from each other. Just like an arrow up and an arrow down. If you don't get the directions, you're not going to know how to combine them. They're vectors. Direction matters. Now, at this point, if I want the net force, so something you all are going to be mostly, it depends on the problem. These are vectors. So guess what? If you want net force, you are going to have to do it in the x and the y. I'm just going to write net force up here for now, but remember, these are vectors. Vectors you can't just add willy-nilly. You got to break them into x and y, unless, in this case, they're parallel. In this case, we're in one dimension. In and out, that's fine. You can add in and out. I cannot add in and to the right. Vectors. All right. So, how do we get these forces? In this case, remember, F equals I times, okay, I'll write the whole thing, I dl cross B. But remember, if your L points always in the same direction with the same angle, so in fact, we're always going to kind of write this like this, dlb sine theta. If everything is a constant, if you have a straight wire, then the force just equals I times L times B times sine of angle. If you have a straight wire, element 2 is a straight wire. Element 3 is a straight wire. If they're not straight, you have to integrate, or if something varies with location. All right, so F2 is going to equal I times its length, I1 times L1 times the field times sine.
When do you switch to what?
The length of, good question. Thank you. 2. Great catch. Times sine of theta, we'll call it theta 2. What is theta? It is the angle between the current and the field. I'm going to write both of these. Yeah, I want you all to think about this. See if you all can figure out what numbers I should be plugging in here. So think about it. When you have an answer, don't shout it out because it'll ruin it for everyone else. I want you all to focus on these angles right now. What should the angle be between this 2 and the magnetic field? What should be the angle between this 3 and the magnetic field? Think about it. And then I'll tell you the answer in like 30 seconds or so. Whenever you're trying to find the angle between two vectors, put their tails together. So I'm going to copy all this to the next page. I need some more room. Always give yourself space when you're solving a problem. All right. So I'm just going to draw this down here. My current is moving upwards. My field is moving to the right. This is length 2. So what is the angle between these? 90 degrees. Let's do the exact same thing for current 3. Draw your vector. There is my vector for 3. Draw your field. You always draw their tails together. Always draw their tails together. Whenever we talk about the angle between vectors, you need to draw it like this. If you draw it with the tail down here, that is wrong. That is not the angle between two vectors. The definition of the angle between two vectors is the tails together. We are solving for this angle. Now, in the picture, I did not give you that angle. I gave you that this is 35 degrees. So theta 3 is going to equal 55 degrees. Why? 90 minus 35 is 55. Or is 55. If you don't draw it, if you just jump and be like, oh, that's the angle of the problem, that's it. Draw things out. I cannot stress this enough. If you do not draw things, you are not doing what 99% of good engineers, computer physicists, everyone else is doing. People that have been, you don't get to a certain point where you're like, I don't need to draw stuff anymore. You never really get to that point. You just get to the point where you realize, man, I sure wish I'd drawn stuff more before. You just come to appreciate it more. All right, so F2 is going to equal, in this problem, current in series is the same. And the problem, I give you the current is 5 amps. I give you the magnetic field is 0.15 Tesla. So you just put in the numbers. 5 times 0.15. Oh, the length. I need to put the length. The length is in centimeters. So this is 0.16 meters. This length on the other side is 0.20 meters. Don't forget your unit conversions. This is something I commonly saw on the free response, is that people forgot to convert units. I don't put unit conversions on the test to be mean. I put unit conversions on the test because that's how the real world works. We're not measuring everything in meters. We're not measuring everything in even just newtons. It's often micronewtons. If y'all, you got to be able to convert units. It's how the world works. Things aren't always given in base units. In fact, they very often aren't. All right, so sine of 90 is just going to be 1. So that spits out some number. F3 equals 5 times 0.2 times 0.15 times sine of 55. That spits out some number. I'll plug it in real quick. There's one last step. Once we get these numbers, we're not done. We need to combine them. So this first one is 0.12 newtons. The one on the right is 0.122873. And then I'm just going to shrink everything so I can put the last step on the slide and not have to make a new one. Oh, notice again I didn't put F1 or F4. The sine of the angle was 0. Sine of 0 is 0. Mathematically, that's why these are 0. Theta equals 0. Sine of 0 is 0. Great. All right, so if I want F net, we are blessed. These vectors already line up. We don't have to split into components. Yay! They're already in component form. Now, you get to make a decision. Do you want out of the board or into the board to be positive or negative? Does it really matter? No. I'm just going to go ahead and say out of the board is positive, and I'm going to say into the board is negative. I'm going to make that decision. So we're going to have negative F2 plus positive F3. Why? F2 is into the board, so we're going to call that negative. Out of the board, positive. So I get negative 0.12 plus positive 0.122873, and the math here is really, really easy. It's really nice. So we get positive 0.002873 newtons. What's the direction of this? Out of page. How do we know it's out of the page? It's positive. We define positive as out of the page. Once you make that decision, just be consistent.
How would this change if like the wire was in parallel, not series?
Oh yeah, you would solve for each one. So if they're in parallel, the question was what if they're in parallel, not series, they could each have different currents. Yeah. In that case, they wouldn't be connected though, and yeah, I'm not gonna do that. All these problems is a single continuous wire. Yeah. All right. Okay, so this next one, I'm not going to expect to get through both of these. I'll try to get through one of them. The rest of the other will roll into Tuesday. That's fine. How do we find the force of a wire that is not straight? Or where the magnetic field varies in location? Those are the two scenarios I can give you. There's only two scenarios. In fact, let me show you. They're on the problem set. A straight wire carries a current of 3 amps where the magnetic field varies in space. Negative 5x squared y hat. That means in the y direction. My magnetic field is not a constant. What does that mean? I'm going to have to integrate. This next problem, my current is not a straight wire. I have to integrate. This next one, my wire is not a straight wire. I have to integrate. These are the only two possible versions I'm going to give you. A non-straight wire or a magnetic field that varies in space. I will do both versions in the class. Today I'll do one of them. Next class I'll do the same. How do we do this? This process should hopefully look very similar to Coulomb's law. First step, draw a picture. Take a couple pieces of wire. Draw the directions of the forces on them. Just like we did with Coulomb's law. Move a little piece, make it dq. Find the direction of the electric field. Similar process. Draw a picture. Next step, write the integral. It's always going to be this integral. Now what do? Replace dl with dx, dy, dz, whatever the direction your wire is going. If it's a curved wire, we replace it with r d theta. Why? Same exact reason we did last time. Break into components. Sometimes you won't have to, sometimes you will. Rule of thumb, make sure you're remembering that. Due to symmetries, only one component will be non-zero. We're only going to generally have to integrate one component. You might have to use a different angle for phi versus theta. Set up your bounds and integrate. Plug in things. I maybe forgot to put things in terms of variables, but actually that's generally kind of done for you. You'll see what I mean when we solve these. These integrals are actually easier to make and actually easier to solve than the Coulomb's law ones. You'll see what I mean. Let's go ahead and try one. All right, again, we got two examples. I'm going to do the straight wire with a varying field. This is the easier one to explain, and then we'll do the curved wire next class. So, a straight wire carries a current of 3 amps in the positive x direction, and a magnetic field given by negative 5x squared y hat. That bold y is y hat, meaning in the y direction. What is the direction of magnitude of the force between some point x equals 0 and x equals 2 centimeters? What if instead the wire was at a 30-degree angle above the positive x-axis? Draw a picture. Here's my wire. It carries some current to the right. How do I know that? It says so. I then have a field. In this field, we're going to pick the origin somewhere on this picture. We're only needing to draw the wire between x equals 0 and x equals 2 centimeters. So this is going to be my 0. This is going to be my x equals 2 centimeters. In fact, I'm going to write it in terms of meters. Do it sooner than later. Never wait to convert your units. This is the only place I need to draw the field. Everywhere else I don't care about. You do it.
What?
Draw the field. You can do this. You all plug in numbers. Make sure your arrows, the size of them matters.
Sorry, I thought you meant do the whole integral.
Oh gosh, no. Yeah, no. Just draw the arrows for now. But once you draw it, feel free to work ahead of it. This problem is actually not hard to, like, mathematically, this integral is not bad at all. You'll see what I mean very soon. For now, I want you to draw some arrows for B, and I want you to draw the direction of those arrows. And it's also good to get a practice of whether they get bigger or smaller as you move along things. Yeah.
I forget, is y the unit vector?
Yes, y here is the unit vector, meaning it points in the y direction. Now, whether it points up or down will depend upon the value in front of that y hat. If the value in front of that y hat is positive, it will point up. If the value in front of that is negative, it will point down. Good question. We only care about the magnetic field where the wire is located. All right, so how are we going to do this? We're going to find the magnetic field on this wire. What's causing this field? We don't know. We don't care. Something is, and it's given by this equation. How do we do this? We start plugging in x values. At x equals 0, my field is 0. At my value of x equals 0.0001, that's going to get squared, gives me a number times -5. That's going to be an arrow down. And as I move to the right, my arrow is going to get squared bigger. It's going to get squared bigger. Because it's less than 1. No, it's fine. It's going down. That's really what I care about. The direction is what matters, is that you know it's down. All right, great. We have our picture. We're now going to pick a little piece of wire. This is always a useful exercise. There's my DL. What's the direction of the force on said wire? Give you all 20 seconds to figure that out. Find the direction on that wire, the force on that wire. So put your fingers in the direction of the current, which is to the right. And then I need to be able to swing this DL so it swings towards the field.
How do you know which way to put your thumb on?
You don't worry about the thumb, you worry about which way to swing it. We will discover the thumb. Your thumb is always at a right angle to your fingers. So, I put my fingers in the direction of DL. How do I get DL to swing? I orient it this way so my thumb points into the board. So what's the direction of the force? Into the board. That is true at every point on this wire. Because they're always in the same direction. Now I build my integral. If I want to solve for f, I am going to integrate I times dl times the magnitude of b times sine of the angle. All right, great. Now I'm going to put in values. Actually, before that, replace L with dx. Replace B with -5x squared. In fact, this is the magnitude of B, no negative. Don't put the negative in there. Our picture is going to give us the direction. The sine of the angle. What's the angle between these? 90. Now, do we need to break our force in x and y components? It's already in one direction, so we're actually spared that step. So the only thing left that you have to do, and actually put the value of this is 3, you just put your bounds. 0 to 0.02. This is a very easy integral to solve. What's this integral? It's going to be 5x cubed. Evaluated from 0 to 0.02. Plug that in and you're done. The 3's in front, so it canceled out. Yeah, it's a great point. I kind of zoomed through that. So 0.02 cubed. And my force is going to be 4 times 10 to the minus 5. And what direction? Into page. And the straight wire ones actually aren't bad. The curved one, there's a little bit extra steps we got to do. We'll do that one next time. Make sure you're practicing, y'all, and I'll see you on Tuesday.
Can you go back to the example with like a straight line?
All right, everyone. Hello, I've returned. We'll start with the joke this time, and then I'll do logistics.
Alright, the joke for today, I took the shell off my racing snail to try and speed him up. It just made him more sluggish. Ooh, thank you.
Alright, so hello, I returned. I am pretty good. We'll call it 98%, basically 100% back to feeling normal. However, I am going to exist back here for pretty much, I'll exist back here / I might like walk around the peripherals during stuff. Out of an abundance of caution, I don't want to pass this on to anyone. So when we do problems, I'll stay away from you all from a distance and I'll have a mask on. But to that end, we're not going to do the lab today for the same reason. I really don't want to be like getting in close proximity to you all because I don't want to be passing it on and grading the labs with only 2 people. And not being able to help you all is not ideal. It would just mean me sitting here watching you all do the whatever. So we're just going to we're not even going to move it to Tuesday. We'll just kick it down the road, which worked out fine because we had some gaps with labs anyway. So all is well. We'll still do the RC circuit lab. It'll just be next week. Then we have 2 magnetic field labs, works out well. And then we have 2 optics labs, which works out well for the end. So, yay. Okay, so that's that element of things. A bunch of things to kind of update you all on. The grades for so I'll talk about this in a second. I'm just going to hide it for now, otherwise you're going to be reading it. I know how that works. The grades for the free response I will have posted tomorrow. So I've got all those from your wonderful grader. I've got all the ones I graded. They're fairly decent. They're fairly good. I think the average is pretty similar to the average for the multiple choice. The reason is, we'll say we're fairly generous on the grading, mainly because that's how the rubric is defined. If you just wrote what you're solving for and you drew a picture, that is 3 points. If you wrote the right equation, that's 2 or 3 points. Like, it's really not hard to get some points and that's why. So to that end, there's generally almost never a curve on the free response because there's so much flexibility and also kind of resolution on the grading. Resolution meaning like we can get fine detailed and actually give you the points based on your understanding. And there's definitely enough time and all that stuff, and you get a choice in which problems to solve. So if there's any that like say I didn't prepare you well for, you just pick a different one. And that goes well.
Will we get the actual paper for FRK?
Will not get the papers back. You can come to my office hours if you want to see it. I keep the physical papers as a physical record in the off chance that there's ever any disputes on grades. I have the physical record to kind of like say, no, this is it, here's why, all that kind of jazz. But you're welcome to come by my office hours sometime next week if you want to see your free response and what you got and why. And at that point, you can take pictures of it. I will still keep the physical record. Again, just so I don't run into any grading disputes. It's just, that's the main reason, honestly. Another reason, it's a pain in the butt to pass out 100 exams. But the bigger one is the grading disputes. That's honestly the main reason. Okay, so there's grades. Obviously, I wasn't here last class for reasons aforementioned. What I am going to do, because this was requested in my lecture class, sometime either Friday or Monday, I will do a recording of the content that was covered. So through slides 23, I'll do the recording. My lecture class also got to slide 23. So I'll do a recording. It'll be just an hour, 20 minutes. So it's not going to be because 2 hours and 50 minutes is a lot of time. Anyway, that'll get through everything. It'll be me solving things. Great. So all that will be done. We're going to cover some of that today. We're going to kind of rehash some of it today. We're going to use some of it today. But yeah, I'll do that recording. It'll be posted on YouTube. I'll let y'all know when that happens. I also will likely extend my office hours on Monday by an hour to account for the hour that I missed on Tuesday. Wednesday, I held the virtual ones. No one showed up. That's expected. Virtual is just not as good. But it existed. I was in the room. I was there. Anywho. So, great. There's that. The next thing I want to point out was the document that was kind of open here, and then I hid. So I told you at the beginning of the semester, one of the things in our syllabus is the professional development activities, but tied to that is the AI activities. And then I haven't said anything about the AI activities the entire semester. Well, now I'm finally getting around to making those, and I'm working with another teacher, Dr. Doty, to develop these. At this point, it's just going to be kind of 2 activities, and I'll outline what those are in just a second. But let me first give you all the reason why. In my opinion, and in the opinion of corporate America, AI is a thing, a very important thing. There is far too much money being invested in it for us to not. And also at this point, if you've used it, you realize this is something different, something meaningful. I kind of compare AI, it's what I'm going to call a disruptor. Disruptor not in a bad sense, disruptor in a sense of something that changes how things are done. The internet is an example of a disruptor. When the internet kind of started to become a thing, if you knew how to use the internet, you were able to do things quicker, more efficiently, potentially more effectively than those that did not know how to use the internet. Before that, it was computers. Computers existed before the internet. Computers were a disruptor. When computers started to exist, same thing. Those that knew how to use computers could do things that people that couldn't. They could do more. So on and so forth. You know, way back when learning to read. Written word was a disruptor. Whatever. Why do I mention this? I think it is important for us to, as a part of university, is preparing you all to use these resources. And so these 2 activities are how do you actually use AI well? Specifically, the 2 activities are going to be within the context of learning. Learning in a field such as this, problem solving, critical thinking, that kind of thing. So, to that end, the first kind of assignment is going to be using AI to help solve a problem in a way that's not just copy and pasting the problem and then hitting enter and then looking at it. Because that is often how it is used. It is often used in the same way Google is used, which is put something in there, open it up, look at it, try to make sense of it, move on with your life. That is not an effect. That is one way to use AI, and that is very effective if you want just facts, if you just want information, if you want to memorize something. If you want to learn how to do a process, you need to engage with it. You need to have a kind of a back and forth. AI is unique compared to Googling things in that you can have a back and forth. It, serves as kind of like a human, quote unquote. You can have a conversation with it. You can have a dialogue with it. You can ask it questions and it can give you responses that make sense to that question. So to that end, that's kind of, we're making a handout. So this is kind of a little preview of the handout. It ideally will be kind of finished up and postable by this Monday, at which point I'll also have the assignment and I'll walk you all through that. So this is just a preview of said assignment. And basically it starts off by kind of showing you that there's levels of learning. And these levels we kind of correlate with using AI. The first level is the way that most people use it, passive. You ask it a question, it spits out an answer. You say, great, I got what I need. I move on with my life. That is kind of the base level of learning. It's just facts, memorization, information. You don't actually engage with the information. You just read it and call it good. The next level is so it's kind of like watching someone drive a car. I've been using the driving analogy a bunch. You watch someone drive a car and you say, great, I have a sense of what driving a car is like. Do you actually know how to drive a car? No. But you at least have some base information. They turn a wheel this way, it goes this way. Great. Next level is they're starting to engage with it. Now you're a passenger in the car. You're actually maybe responding to things. You're seeing things in a higher detail. You're actually checking maybe some of the information, but you still are not actually doing the activity. The third level is the level I want you all to be in, and I want to help you all support you in being. And this is kind of the learning level. This is you being a driver, but maybe using some of its assistance. Maybe this, so you can think of it two ways. Maybe you remember when you're getting your permit, you have the person next to you who's giving you guidance, but you're the one actually at the wheel. And the example I gave here, I said having like a lane assist or cruise control on. Your hands are on the wheel, but it is still doing kind of some of that work for you. But you're still the one driving the car and you're going to experience it. These last two levels, I do not expect you all to engage with in this class. This is once you understand it, using it to make new things. Developing new things. This is something you do want to get skillful at. It is just far beyond the context of this class, because for you to be a creator, for you to supervise it, these last two mean, these other ones, it's kind of a hierarchy of who's doing the most work. At the top level, it's doing all the work. At the bottom level, you're doing most of the work, and it's just providing that little bit of like guidance and assistance and things like that. We're going to be somewhere in the middle. You can't get to that high level. You can't be the one doing all the work unless you kind of know all the information. So in some ways, I use AI kind of in this creator level to make problems, make multiple versions, things like that. I check through them. I moderate them. I give it specific parameters, all that kind of jazz. So the next kind of things are tips on how to do that. And so again, this document will be posted. It's still getting kind of ironed out. But the first thing is don't just copy and paste the question. Put the question with a follow-up in the same thing. Before you hit enter, ask, so like some of these are use guided inquiry, ask it to use guided inquiry, ask it to act like a tutor and guide you through the problem. Tell it, hey, I want to solve the problem by this process. Is this a correct process? Say, hey, I tried solving it this way, but I got this answer. Help me identify what's wrong. And this last one, which I was super impressed with, I tried this out today. Hey, here's a picture of my work for this problem. What went wrong in this? Every single thing I'm mentioning here is how I work with students. This is the kind of things when people come to me, this is what I do. When they come to me and they ask me how to solve a problem, I don't just tell them how to do it. I ask them questions. That's kind of those first two bullet points. If they've already worked on it some, I say, hey, show me your work. And then I kind of ask them questions about it, or I point out, hey, you missed this, or you forgot to put a squared here, or something like that. So using AI in the same way, that's all of this is trying to teach you how to engage with it the same way I engage with students. And this last one I was super impressed with. So if I jump over here, if you're like, what's this? This is me adjusting grades. Don't worry about it. I'll explain that if you're really curious, but it's not a big deal. It wasn't anything confidential. Don't worry. I never put any of your all's information into ChatGPT. I do want to mention that. Technically, the license I have, they say they don't keep my data. Do I really trust them? Don't worry. I'm never putting any confidential or your all's grade information or anything like that into these things. That's an important thing to keep in mind. Privacy of data. All right. But what I want to show you all is how I used it. I had a student not in this class ask me how to solve a problem involving a bunch of resistors and how to solve the current through one of the resistors. And so I worked out the problem myself and I sent him a picture of it. So this is the picture I sent him. It's going to look like a bunch of nonsense. I mean, maybe parts of it you'll recognize. He had the context for this problem, though. The student did. I literally just told ChatGPT, here you can see the prompt I gave it. Hey, I want to test your ability to read handwritten work. Analyze this image and tell me what you observe. And it did a really good job. I was super impressed. It said, hey, this image shows a series in parallel resistant being reduced step by step. And it ultimately is one resistor. All the numbers it was able to pull from my handwriting. It was able to determine the math I did and also do the math itself to kind of compare it. I was super impressed with its ability to read handwritten work. To that end, this saves you a lot of effort. So this is something when I work with students, the first question I say is, show me your work. You can actually just take a picture of your work and send it to ChatGPT. And that's ridiculous that it's able to do that, but it is able to do that. Like it's kind of wild. It's gotten to that point. It is not perfect though. So that relates then to the next kind of bullet point. Oh, that's the problem set. The next kind of bullet points are make sure your question's clear. Something you're going to learn the more you engage with AI is if you don't give it enough information, it will ask you for more information. It will just assume things. Just like humans. Well, humans will and humans won't. Sometimes humans do. Sometimes they ask follow-up questions. But it's one of the big downsides of AI. AI, if you give it just a little bit of information, it's going to make so many assumptions, but it won't tell you what assumptions it makes. and it will assume every assumption it made is completely correct 100%. It's a big problem. If I tell you to go to the grocery store and buy me some bread, that's might sound like a simple request, but there's a lot of decisions there. As a human, if you think through that process, you're going to realize, does he want me to go to a certain grocery store? Does it need to be organic versus non-organic? What kind of bread? Does he mean sliced bread? Does he mean like a baguette? Does he mean buns? AI doesn't know to ask follow-up questions. Humans do. One day it'll probably get better at asking those follow-up questions. But if you don't provide it the clear detail of I want you to go Publix and buy this brand of white bread for this price, if it's lower than that price, don't pay for it. It doesn't know, generally. So anyway, be precise in your wording. Then follow-up questions are useful. Why did you do this? Why did you choose this equation? What if I change this instead? What if I instead, could you give me a different version of this problem where I'm solving for this variable? What if I use this method and not the method that you showed? You can do this stuff with it. And then the last thing is you got to make sure it's correct. My experience with this, with ChatGPT, I have the paid model. All the others, look, I am mentioning ChatGPT. Do not hear me as a shill for ChatGPT. It's just the one I have the paid model of. Use whichever one. The rule of thumb for AI currently is use whichever one you have the paid version of. If you have a paid version of it. If not, pick your favorite. But almost guarantee if you're paying for one of them, it's better than all the other unpaid versions. That's just kind of a rule of thumb currently. Make sure it's correct. It's about as correct as I am, has been my experience. Meaning I make mistakes. I've made a lot of mistakes in front of you all. AI is going to make these models, they're going to make a lot of mistakes as well. How do you know when it makes a mistake? Every problem I give you all the answer to. When you give it a problem, do not tell it what the answer is. Have it actually solve out the problem. Sometimes when you give it the answer, it will just spit out a bunch of things, but it will not actually do any calculations. If you don't give it an answer, you are forcing it to do the calculations, and thereby it's more likely to get the right answer. That's been one of my experiences. Don't give it the right answer. Otherwise, it might say, hey, do this. And you've actually seen me do this in class sometimes, where I say, hey, here's a setup, and if you plug this in, you're going to get this answer. And every now and then I've made a typo, and it turns out when you plug in the numbers, you don't actually get that answer. It's the same exact mistake AI does sometimes. I've even had it write the right equation, but if you plug what it wrote down, it gets a different answer than what it got. It makes mistakes, like a human does, because it's trained on human data. Wild, right? Anywho, some things you can do. Again, baseline. Use my answer as a baseline for what's correct. Ideally, my answer should be correct and double check. There's always a chance they aren't, but generally, if there's a typo, someone has spotted it and notified me, and I've updated it before you've gotten to that problem. It's very likely the case. In the case where you don't know the answer, or if you're not confident in it, so this is where it gets trickier, ask it for sources. Ask it for websites, videos, resources. Where did it find that information? Now, we are getting to a tricky day and age. Really good YouTube channel called Cursigeist. I'm butchering the pronouncing of that. They recently just did something and they titled it AI Slop, Death of the Internet. Very dramatic. Something that is going to be slightly concerning and something for you all to be aware of. They raise a really good point on this. So where does AI get all its information? Online. What are people using AI to do? Make stuff that goes online. Hopefully you can see that this is a bit of a cyclical loop. And so what happens is if it grabbed wrong information and then someone uses that information to make another resource and then the next AI model pulls from that misinformation, you end up in this cycle loop of incorrect information. And you can never get back to the beginning of it because it gets lost. It's getting to the point where people are potentially even using it in research, and that's where it gets really scary. Because ideally we look at research as primary sources and the utmost trustworthy. And so the more that AI may intersect with that and people rely on it too much for that, it can get a little dicey there. Anywho, just something to be mindful of. Not every YouTube video nowadays is done by a human, which doesn't mean that it's going to be wrong or right, but just something to keep on your horizons, that the internet's getting to be a bit of an interesting place now because of this, or it's going to develop in this way. Anywho. Watch the video by Cursigeist. It's really good. Recommend it. To that end, great. Here's the kind of rundown. Way more time than I'll spend more. Tuesday, I'll talk about it. But the first assignment will basically just be have a conversation with AI to solve a physics problem. Have multiple prompts, have multiple questions to it. Pick something. You can pick any question you want. It could be a question in this class, it could be a question in your other class. I really don't care. It needs to be a question you don't know how to do, though. Otherwise, you're not. If you already know how to do it, you're not learning. And that's the whole point, is to practice using this to learn. It'll be graded on completion, very straightforward, just like I'm not going to go through and read all the logs. We're going to have you submit the logs just for funsies. But it'll mainly be asking, what prompts did you give it? What problem did you give it? What follow-ups did you give it? And then just kind of submit the whole log with the AI thing. Very straightforward, very simple. And why am I doing this? I sincerely believe that we have to train you all how to use this well. Like anything, I'm training you how to teach, how to think. This is such a big deal that I think we have to spend at least a little bit of time practicing using it in the context of your discipline. Physics is relevant. The way of thinking at least is. All right, that was long-winded. Tyler, Angelina, comments, thoughts, suggestions from your all's perspective regarding AI and physics and learning? And
I found it very useful myself. I mean, I think it's here to stay.
Use it, but trust it with some critical thinking involved.
I've had it make a lot of mistakes. And again, not a lot, but as many as I make, which is still a good amount. So it's been really, I've used it to make multiple versions of your problems. Every single time it makes a version, I double check the answer. And there's about a 1 in 10 chance it's wrong, which is kind of interesting. Even when it knows the process. Just it makes mistakes. All right, long-winded monologue over. Okay, so I do have the worked out answers to everything kind of from last class. So I'm going to use this PowerPoint to kind of walk through this. I will upload this PowerPoint for you all. See, ta-da, it's got the worked out stuff from last time. And I think he might have showed you this as well. I do need to, if you look really closely, you'll see the answers for the next one. Oh, look, it's gone. Oh, look, it's gone. Oh, look, it's gone. I forgot to delete these last ones. Not a big deal. All right, so let's do a recap. And we're going to maybe practice 1 or 2 of these things. History, yay. Magnetic fields exist. This is going to be really quick. I'm not planning on reteaching the whole class last time, but I want to point out the main points because we're going to use them today. Magnetic fields exist. The variable is B. The unit is Tesla. Great. This symbology is important. I have the direction here. I have this great little technique that I still use. Bow and arrow. If anyone's ever used a bow, you don't have to have used it. You've seen one. An arrow. It's got feathers at the back. It's got a point at the tip. How do you determine this? How we look at this? If an arrow is coming out of the page, meaning it is coming out of this board towards you, what do you see? The tip of the arrow. What do you see when the arrow is going into the page? You see the feathers at the back. You see a cross. That's an easy way to remember which of these is which. I still use that technique to this day. Yeah. It doesn't mean, this just means an arrow. So this, out of the page here, literally imagine an arrow jutting out of these screens. Whereas into the page means an arrow jutting, pointed into it. So we've talked about vectors in this class, and it was very easy for us to draw, I want to say in the x direction, I draw an arrow to the right. Positive x direction. Easy. If I say positive y direction, I draw an arrow up. Really easy. No problem. We need to work in 3 dimensions with magnetic fields for reasons that will become clear as we kind of go through these things. X and Y are no longer sufficient. We need a 3rd dimension, into the page and out of the page. The problem is drawing an arrow into the page is awful. Look, this is my arrow into the page. Does that look like that could be up, that could be, it's not clear at all. So how do we make it clear? We do a circle with a dot to kind of show that's out of the page. Into the page is that X, and use that arrow analogy. Something you are going to need to know. This is very, very common notation for clarity's purpose. All right. Moving charges experience a magnetic force. Why? Because that's how the world works. That's the answer to that. This is an observation of reality. This is a law. This is someone observed this.
It is equal to QV cross B, which can be a cross product simplified to QVB sine theta. Theta is the angle between V and B. We're going to see this later today. Right-hand rule. I can almost guarantee this doesn't make sense to half of you. Not because of an insult to you all, but because this is notoriously one of the topics that people have challenges with. It just always. And it's one of those things that once it clicks, it's going to be really easy for you. It's either you know it or you don't. It's literally that, like, this is fairly dichotomous on whether you can do this. So, to that end, I did a nice little diagram here where I took pictures of my hand because drawing pictures of this is awful. So just to kind of walk through this example here, and I'm sure he did this in class last time, but seeing it twice hopefully is helpful. The technique, you always start with your hand making like this L kind of thing. Your thumb needs to be perpendicular, like this is where you start. It's called the right hand rule. Very important, use your right hand for reasons that will be explained after we do it 1 or 2 times. You have to use your right hand rule or you get the wrong answer. So we start with this. We point our fingers in the direction of the moving positive charge, or just in this case, moving charge, just to say moving charge. Your goal, and I call this the swinging door method. That's my name for it. I don't know if anyone else calls it that. Your hand, your fingers can only bend in one direction. You can think of your fingers like a door where your knuckles are the hinge. It is only possible to bend your fingers in one direction. Now, if you have the ability to hyperextend your, so I'm very flexible with my hand for reasons, like I can bend my fingers backwards pretty easily. Most people can't. So most of you, your fingers can't really, they can really bend backwards. Yours can't, very likely. This is convenient for us that your fingers can't bend backwards because that means you won't make a mistake on this. Your fingers should only be able to close one way. Like a door only closes one way, right? Great. You can't bend them, sideways. You can't bend them this way. This is very important to us. Why? We're going to take that velocity, and based on this picture here, our goal, the technique here, is I want to swing this velocity towards B. I want to take that velocity vector and swing it so that it points in the direction of B. So pretend that your fingers are the velocity vector. We start in the direction of B, which is going to vary based on what side of the room you're on. So pick a projector and use that one. I'm going to pick the one directly in front of me because it lines up with me. I put my fingers in the direction of B. I need to swing this V vector towards B. B points down. My fingers currently cannot swing down. It's not happening. I can't swing them down. If I rotate my hand this way, they still can't swing down. My fingers cannot swing backwards. If I do it this way, they still cannot swing down. Only when I rotate my hand this way. Notice at all points, my velocity is still pointed to the correct direction. When I do it this way, I can swing my velocity towards B. I can swing it towards B. What's the purpose of this? My thumb gives me the force. Your thumb gives you the force. That's the point of this. We're trying to find the force on this charge. How do you do it? Right hand rule. If you get really good at this, you can kind of do it in your head. But I still myself use my right hand rule. It's just easier. It's much easier to do this than to try to visualize it in your head. All right, we're going to practice this today, so we're going to see how it goes. And again, I know this is notoriously difficult. This is true of a positive charge. A negative charge, your force is exactly the opposite direction. Remember, negatives always do the opposite of positives. That's just a rule. Now, to that end, I told you, do not use your left hand. Go ahead and use your left hand and see what happens here. Try it. I got a velocity to the left. I got a magnetic field down. I want you all to find the direction your thumb points when you use your left hand, when you use the incorrect hand. See what happens. And you know what? Let's just make this a question. I want to see if you all know the right answer. I can't go around and talk with you as much, so the velocity of a charge is to the left. The magnetic field is pointed down. If you accidentally use your left hand, what is the direction of the force? And this is going to be a positive charge. Is the force going to be up, down, into the page, out of the page? Draw these arrows on your paper. Draw them somewhere. That is one of the best, as I've told you all a million times, drawing a picture is the best way to get an answer right. If your picture stinks, your problem's going to stink. Oh, and whenever I say up, down, left, right, this is what I mean. This is going to be true for the rest of this class. Up means to the top of the paper. Down means to the bottom of the paper. Left means left. Right means right. In means in. Out means out. This is the wording I'm going to use for the rest of this class. It's much easier than using XY. Well, XYZ has its own complications. Now I get to walk around the peripherals with a mask on. Good old COVID days.
Here. Page left. And it says magnetic field is pointing down. Oh, you're so right. It is.
Okay, move to the left. I gotta work this out too.
And then down.
Yeah. Okay. Yeah.
I know, I'm gonna be sick.
All right. Give you all 5 more seconds. I think you pretty much got it, if you got it. So 5, 4, 3, 2, 1. Something that's very important is that you actually draw this on your paper. Why? So you can make your hand line up with the paper. If you use the board, that can kind of work, but on the test, it's going to be drawn on your paper. You're going to need to draw it on your paper. You'll see what I mean once you eventually do it. So we got our velocity this way, our magnetic field's this way. Again, I'm drawing it out, and then I make my hand match my picture on my paper. So y'all can't see this, but on mine, I'm lining up my hand with V. I swing it down, and now I use the right hand. Again, it gets a little awkward at times. You got to kind of like convolute things. So I put it this way, I swing it, and my thumb points into my computer screen. That is into the page. So into the page is the right answer for this, and that is incorrect. Like that is correctly incorrect.
Correct for this answer.
Yeah. If you accidentally use your left hand, what's the direction of the force? Note, this is opposite the direction of the actual force. So, if you use the wrong hand, you get the wrong direction. Fun fact for you all, another way of thinking about this. This is a positive charge. If you really want to, another thing you can do, if we use our left hand, you'll notice you got the opposite answer. What do we say about negative charges? You get the opposite answer. So your right hand is for positive charges. Your left hand could be for negative charges if you really want to, because it gives you the exact opposite. You can really easily prove that. If I got a velocity up and a B into it, look, I curl my hands the same way. My thumbs point opposite directions. So to that end, Be careful. Most of you all are right-handed. Not everyone. Why do I mention this? Why is this relevant? On the test, you're very likely holding your pencil in your right hand. And so you're solving the problems holding your pencil, and it says, find the direction of the force. And you're like, well, my right hand's holding a pencil, so I'll use my left hand. And you get the wrong answer. It's a very easy mistake to do. You don't just pick whatever hand's free. This only works. This is the definition of cross products. I didn't define the rules. I just teach them. That's how it works. Why was it defined this way? It very likely might be because most people were right-handed. I don't actually know, but it's maybe an interesting theory. All right, great. Look, a bunch of wrong examples. Practice. We're going to practice some more. It's going to be great. All right. Another thing you all learned is that charges that go in a magnetic field, they don't speed up, they don't slow down, but they do change direction, and they make a circular path. Why do they make a circular path? So an example here, again, I'll go through this more. At this exact moment, the force is upwards. A little bit later, the charge will be up here, and its force will be inwards. The force is always perpendicular direction of motion, so it makes a circle. This is actually very, very useful. Basically, it means that we can redirect charges. Some examples of this he mentioned last time, but one that's not mentioned here is the old cathode ray TVs. So way back when, currently TVs use LEDs of varieties of types, or LCDs. Way back when, how did TVs work? Is they had an electron source, so they shot a bunch of electrons, and then they had a phosphorescent screen in the front. Now, the problem is you needed these electrons at a specific spot on the screen to make an image. How did they do that? Magnetic fields. So these old cathode ray TVs basically just take a bunch of electrons, and then they use magnets to steer them where they want them to be. And they scan lines on the TV at a rate of making a screen, one every 60 seconds. That's why those old TVs are thick, are wide, because they literally need enough room to launch a bunch of electrons and then steer them where they want them with magnetic fields. So, fun facts. The Earth's magnetic field, hopefully chat about that with you all. Northern lights, all that good stuff. The charges literally get trapped in the magnetic field and spiral along them into the northern atmosphere. That's why you only get the northern lights, because the magnetic fields intersect with the north. You get southern lights a little bit as well. You just get the opposite charges that are doing that. The sun is projecting positive and negative charges at us. It's fine.
For the speed of the charge moving, the tangential speed's the same, but it'll change translation.
Yeah, that's a great question. The tangential speed is the same. Yep. A magnetic field cannot do work. A magnetic field cannot cause a charge to speed up or slow down, only change direction. Now, I'm going to go ahead and give you the counterexample. That's going to be, I can't even explain to you why, because it's incredibly complicated. I told you that a magnetic, it does not speed. It's very easy to just show you it does not speed them up or slow it down because the force is always perpendicular. Anytime you want to speed up charges, you need electric fields. That's something important. Or a changing magnetic field. We'll learn about that in a couple weeks. If you have a static magnetic field, it cannot speed them up or slow it down. If you have a changing magnetic field, then it can. Future things. All right. Circles, yay, circles. Hopefully you all remember centripetal force. Great, there was a problem. Grady solved it. Great, cool. All right, that was a quick recap of yesterday. And way quicker time than I expect you to understand it. Anyway. Okay, really, really simple thing. If I have one moving charge, great. What if I have a bunch of them? That's just current. What is current? Current is a bunch of moving charges in a wire. So if one charge experiences a force, then a bunch of charges experience a force. Not a big jump in logic here. If one thing happens to it, then they all do. And you know what's convenient? Current's defined as moving positive charge. So we can use right-hand rule. Cool. All right. The derivation is very simple. Very, very simple. Just a handful of steps. So we have F equals QV cross B. We remember the definition of V is dx dt. That's from Physics 1. Nothing crazy so far. So we have F equals Q times dx dt cross B. All right, cool. Now what? What if this charge is, I want a really, really tiny piece of this charge? Really, really, really tiny piece of it. How do we make it really, really tiny? Yeah, we just put a D in front of it. If you put D in front of something, you made it a tiny piece of that. We want a tiny piece of the, again, instead of having all the force, now we have a tiny, tiny piece of the force. Great. Still got our vector here, dx dt, cross B. Through the magic of algebra, we just rearrange this. df equals dq dt times dx cross B. And now we're basically done. You only need to remember one thing, the definition of dq dt. dq dt is just I. And that's our new equation. Except instead of dx, so remember in the past, we used to call, we actually did this backwards. We're going to call, instead of dx, we're going to call it dl, where L is the direction that the current's flowing, direction of the wire. We did this in the past where we went from dl to dx. You can do the same thing the other way around. So there's the derivation. Boom, there it is. We use lowercase l, capital L, it really doesn't matter. So this is the force on a tiny piece of the wire. dF equals I, dl cross B. A cross product can be written as this multiplication of the terms times sine of the angle between them. Direction, you got to use right-hand rule. Same thing. So we're going to get to practice it even more today. If the wire is straight, meaning that the angle is a constant, and B is basically, if everything's a constant, you pull it all out and you get just IL cross B. If everything is a constant, I gets pulled out, B gets pulled out, sine of theta gets pulled out. You're just, what's the integral of dl? It's L. So we're going to see both cases today. We are going to do cases at the end of class where we're actually integrating. We're going to start off with the simpler cases, though, where we're not integrating. But it's not going to be anything too bad. And just remember, y'all, this cross product. I do not expect you all to know how to do a cross product. I mean, you have learned this or are learning this. The purpose of this class, I need you to know a cross product is the magnitudes of the terms times sine of the angle between them. In your all's other classes, you all might have seen something like this. You have to set up this matrix to do a cross product. If you don't recognize it at this point, you haven't seen it yet. But don't worry about it. You're not going to have to do it in this class. It is the more robust way of doing it, but I'm not going to teach it. I'm not going to bother with it. This is good enough. Okay, practice. Let's see if y'all can do right-hand rule. It's the exact same rule, except instead of V, it's I. Same exact process. What is the direction of the force in a wire carrying current to the right and a magnetic field pointed into the page? You are going to use your right hand because current is defined as positive charge moving. So great, we get to use our right hand. Is this force up, down, into the page, out of the page, or no force? Mark the last one right. And I'm going to go around. Yeah, the tests are always fun because you're going to see everyone doing this right hand rule thing. It's going to be a great time. If you don't have it on your paper, draw it on your paper.
Come up with
Yeah.
Yes. I think it's because your job is down with like the screen, so I have to start out.
Oh, sorry. Here.
You said it, right?
Yeah.
Yes.
I can do like a pro sheet, but I also do
That's why it's like you have to use
All right, 10 more seconds.
All right, in 5, 4, 3, 2, 1. All right, again, draw it on your paper. You put your fingers in the direction it. On my paper, that's to the right. And then I need to swing it. I got 2 arrows here. I need to make the current swing towards the B. When I make it swing towards it, my thumb points up. So that's the direction of the force on this wire. Now, that is the force everywhere on this wire. This entire wire will want to move upwards. Yeah, I'm not going to get too much into the weeds there, so that's fine. All right, great. This was really convenient because it was a nice straight wire. All right, do it for a non-straight wire. Here's the technique here. I give you a hint here. Find the force on a small piece on the left side and a small piece on the right side. Then use symmetry. I will highlight 2 parts for you. You need to know the directions. So here's a tiny little piece here. I'm going to call this DL1. It is a vector. You need to decide which way that vector is pointed. I just made a line. It's not an arrow until you add an arrow to it. You need to decide what the direction of that arrow is. I then pick a part on this side. Exactly the same kind of height. And again, I did not draw the direction of the arrow. Draw this out. Draw the arrows. Find the force on each of these. Then use symmetry. It's pretty much what every physicist, it's always, find a piece, then use symmetry. Always symmetry. If there wasn't symmetry, it'd be more unpleasant. Physicists love spheres and circles. You'll see what I mean by symmetry once you start to solve it. For now, just find the force in each of these.
So it is kind of.
They're horizontal, right? The ones on the left, right?
Yeah.
Everywhere along your perpendicular to the bar, right? So every single, like, just like how you drew it. That's all horizontal. Only a straight line.
It's not like the correct way to do it. That's how I did it.
That's and that will work with any two examples. So that all points
I do because I'm not as
All right, if you haven't drawn the directions of current, turn these things into arrows and then find the force on each of them. They're not vectors unless you make them arrows. I just put lines. Now they're arrows. Give you all like 20 more seconds or so. Now what's nice is a lot of people, I've done this question a few times, oh, there's a bottom of it with the force field, and they realize that force is It's actually one of the tricks to solve these that I'll like make a mention of.
Yeah.
So we're going to solve this or something similar to it, the force, actually find the force on this.
Yeah.
It's actually a nice
I think I went through it. This is talking about this one?
Yeah.
Yeah.
There is a trick to solving these, which is really cool. We know that if this was a solid loop, that the force would be 0. So what you can actually
work
do,
backwards.
you could pretend like there's a wire here
Yeah.
with current running the other way.
Okay.
And if you find the force on this piece of the wire, it's exactly equal to the force on that without having to do any of it.
Like if you flip these around.
If you just like pretended like these didn't exist, then you make this a loop where the current would flow. You make a pretend path.
Okay.
If you find the force in that pretend path, it's exactly equal and opposite to the force in that path.
That is fun.
Yeah, right? That sounds like I didn't.
I'm gonna redo it now.
I will make mention of it,
Yeah.
but not like. I'm not going to encourage it per se.
Okay.
All right, 5, 4, 3, 2, 1. All right, so right-hand rule. This first one, the force is going to be up to the left. We're going to call that DF1. It's not the entire force; it's a piece of the force. I really want you all to get used to this D notation. You've used it a lot in your calculus classes, but actually understanding what it is in a physical sense is incredibly useful. All right, that's DF2. Actually, I'm going to kind of draw it a little bit more kind of aligned with these. It doesn't really matter. These should be infinitely small anyway, but I just want them to be the same height. All right, one's up to the left, one's up to the right. If you draw these vectors, tip the tail method. And you can hopefully see this without this, but if not, that's fine. The X and Y cancel. This is true everywhere on the wire. If you all find the force everywhere on the wire, here it's this way. It's kind of like just outwards in this problem. This is not always the case. You cannot apply this to every, like, if the magnetic field was instead to the right, this is not the case anymore. So this is not something you can just memorize. You can't just memorize every possible combination and find and say, oh, it's always good. If I have a loop of current going clockwise in the top half, the force is going to be up. Only if the magnetic field is into the page. What if the magnetic field was out of the page? Then it's the opposite. What if the magnetic field was to the right? Then I'd have to think about it more. Like, I even don't have the answer off the top of my head. So long story short, this one is up. You have to be able to do right-hand rule. This is an excellent problem for like a free response or a multiple choice in a test. Do you know how to do it? Do you know how to do right-hand rule? Do you realize I'm adding up all these pieces? Great question for that. All right. Let's look at some straight wires. Find the net force in the wire below if I equals 5 amps and B equals 0.15 Tesla. So this image here has 4 pieces of wire and a magnetic field pointed to the right. So what we're going to do is we're going to break this up into 4 pieces. That's the kind of this trick here, and then I'm going to let you all do it. So I'm going to tell you the trick. Right now, it's not a straight wire. It's 4 straight wires. If I can find the force on each of these wires, I can add them together. That's the trick. Break the problem into pieces you can do. That's anything you do in life. If it's complicated, break it into a bunch of small pieces you can do. All right, so that's wire, let's call this like piece 1. So this is 1. Wire 2 is pointed up. Wire 3 is going to be pointed down to the right. And then wire 4 is this straight wire here. All right. I want you all to think about it. See if you can figure out how you'd solve. Now that I've broken into pieces for you, see if you can figure out the force on each of these wires. Figure out the directions first. That's a great place to start. Find the directions of the force on each of these pieces of wire, and then go from there. Using that same technique I just told you. Like so you can figure this out.
Right. Okay, so I guess it does depend on the direction of the magnetic field. As long as we're talking about, maybe it works.
Maybe an error in the sign is calculated.
Calculator? Yeah. I mean, if it's running parallel or anti-parallel.
No, I know why. I know. This is gonna sound stupid.
Yeah.
Like this triangle is not correct.
Oh, talking about like the sidelines portion.
Yeah.
Okay.
Yeah.
Because if that was real, it'd be like kind of.
Yeah. But I1 and I4 should be like, and I don't know which one should be up and which one should be down, and that results in a problem. I realize that
because then your finished loop would be kind of like at a diagonal.
Yeah. All right. What's up?
So the direction,
Yes.
I feel like
Yeah, they're both in the same direction. So when they're parallel, this one will actually jump to the equation. What's the angle of two things that are parallel?
180.
Or is it? Yeah, if they're anti-parallel 180. What's sine of 0? Of course, it's 0 or 1. You can't actually swing it at all.
Okay.
If it can't swing at all, the force is 0.
Because I was thinking, like, am I supposed to be swinging in that
There's no way. They're both already lined up, and if they're both lined up, there's no force.
Oh, yes.
Like I'll do all like yeah.
Yes. Yeah. I don't. Whether or not it's negative, I don't care. Okay. As long as it's because at the end of the day, the answer on the launch is the matter of the direction. Okay. So if you say out of the gate, doesn't have to be a positive answer. Okay. That's something like it, but it's a great point. It's all relative. Positive and negative are all relative, as long as you communicate effectively at the
So,
end. So we're used to saying
am I like going in the same direction as you, or am I going to? So like for this one, am I going? Yeah, like am I going? Like should it be like this?
Oh, the directional forces. So you point your head along the direction of this, and then just swing towards the yes.
This way or this?
The magnet field's going to the right.
Okay, so
For that one. That's like,
we're fine. No. Yes. Three is
All right. So first step is the direction of forces. What's the direction of the force on the first wire? There is no force on the first wire. What's the force on the, what's the direction? There isn't one. Why? So I actually am going to mention the equation here. Remember the force is IL cross B for a straight wire. For a straight wire. If it's not a straight wire, you got to do the integral. Don't worry, the next slide will have that. So this is ILB sine theta, where theta is the angle between it. Anytime you all do a cross product, and you're going to do cross products in your future, it's multiplying the parts of vectors that are perpendicular. A cross product is multiplying the parts of vectors that are perpendicular. Just to show you all this, in case, because this is something that I wish had been conveyed to me when I was, you all learn about dot products, you all learn about cross products. And at least for me as a student, I'm like, I have no idea what these are physically doing. I can do the math, but physically, what the heck is a cross product? Here's what a cross product is doing. Look at the math here. It's taking some vector A and some vector B, and I'm multiplying it by, you know what, actually I'm going to write this slightly differently. It's not going to change anything, but it's just going to be easier to convey. Here's vector B, here's vector A. If I multiply B times sine of theta, what am I actually finding? What is B times sine of theta? It's this part of the triangle. What are you doing when you're doing a cross product? You're finding the parts of vectors that are perpendicular and you're multiplying them together. That's what a cross product does. What does a dot product do? A dot product multiplies the parts of vectors that are parallel. So if you want the parts that are perpendicular, cross product. If you want the parts that are parallel, dot product. This is very, very useful for like torque. No one is making something move by pushing or pulling on the object. You gotta push and pull perpendicular to the object. No one is making any work by doing a cross, whatever. There's a little thing there. Long story short though, the angle here is 0. This force is 0. This force is 0. The force here on the top one, that's gonna be into the page. So that's force 2. This one is out of the page. So when you add these forces together, one should be positive and one should be negative. Which one's which? You get to decide. If you decide that out of the page is positive and you get a negative answer, that means your net force is into the page. Just be consistent. At the end of the day, the answer that you need to output is some number followed by out of the page or into the page. The math is going to tell you the direction based on the positive and negative sign that you decided. So go ahead, y'all, find the force on F2. Find the force on F3 using that equation. Then subtract them from each other. Make one positive, make one negative. I don't care which one's which. You decide.
Whatever portion of it is perpendicular to the field. As long as it's
So flux actually was parallel because it was the area vector. Yes, but yes, we are finding we're finding
There are the current
crystal path.
and the magnetic
Yes.
field.
It's finding a part that's perpendicular.
But it's funny, the portion of the leg that's
Of the
Yes,
vector,
they are
like,
perpendicular.
in this case,
Oh,
it's a
oh,
vector.
so it's making it
It's a little different
It's a
for
vector.
us.
Yeah, this L is the vector with magnitude of how long your wire is and the direction of your watt. The current.
Okay.
Yeah.
So that might be
Because
just multiplying to the magnitude.
Yes. Yes. L is those, I need to actually add those magnitudes.
that angle.
You should never.
Horizontal, which is where-
Yeah, we don't put negative signs when we plug in stuff here.
But that's not the angle that separates the magnetic field. That's the angle that separates those wires.
So theta is the angle between the magnetic field.
Between the L or like your L and the magnetic field.
With the angle for 355? Okay. And then do you need to break that into components?
Because it's into the page.
Oh, okay.
Into the page, out of the page is all we care about.
I just know that from the actual vector, the x component doesn't contribute, it's 0.
Yeah.
Right? So,
Yeah,
But
so-
you don't need to do like any cosine after that?
We just swing it. So we're adding the forces.
Yeah.
And the forces are purely into and out of.
Okay.
So. All right, so I wrote the equations here. It's ILV sine theta. Just put in what those are. What is the current through the second path? What is the length of the second path? What is the magnetic field passing through the second path? And what is the angle between the field and the direction of current? That angle is the angle between the field and the direction of current. That angle is different for the second path compared to the third path. Here's the trick. If you want to figure out that angle, take that magnetic field and draw it such that its tail touches the tail of the other one. Make their tails together. Anytime you have two vectors, two random vectors, and I want to find the angle between them, how do you find the angle between them? You draw them so that their tails are together. This is correct. This is not correct. Draw their tails together. Anytime I say the angle between vectors, draw their tails together. So, draw the magnetic field. I drew it for, you can move there. It's to the right. You can draw it wherever you want. You can draw it all over your paper. It's over here, it's over here, it's over here. You know, it's everywhere. Draw it on the tail of 3. That's going to help you figure out that angle if you're having difficulty with that. Because if you think the angle is 35, you're wrong.
Do you have a numerical answer? Or is that
Yeah, the answer to this problem is 0.002813.
Okay. Yeah, perfect.
Out of page.
Oh, wait.
Something like that. I might be off.
It was earlier in the slide.
2873. And there should basically be no rounding. This should be like really easy to get this accurate of a result. Oh, make sure you convert to meters. Base units, always base units. Always base units. Yeah. Don't forget to convert your units. The real world isn't always in base units. In fact, it rarely is.
Yeah, I don't know. I'm doing it quite well. I don't know. I'll use my calculator.
I'm really bad at
Okay, so you want to
Yeah.
I got this
the other one.
Alright, so I'm basically finishing up the problem here. The angle is 55. You can see it in the picture. It's the angle between B and the direction of current. How do I get net force? I add them up. Now, these are vectors. So if any of these vectors were perpendicular, if any of these vectors didn't line up, parallel, anti-parallel, we'd have to break it into components. These are vectors. Now, we are blessed that we only have two arrows in this problem, two forces, and they're anti-parallel, so we can just add them. You can always add vectors that are parallel or anti-parallel. You cannot add vectors if they're not parallel or anti-parallel. Not as is. You got to break into components. That's the whole point of breaking into components, is you break them into pieces that are parallel and anti-parallel. That's the whole reason you all do that. Now, we're blessed in this problem that they are anti-parallel. One's into, one's out of, so I can just kind of subtract them. I'm going to make the executive decision to call out of the page as positive and into the page as negative. Pick what you want. So I get 0. My F2 is into the page, so that's going to be negative. My F3 is out of the page, so that's going to be positive. Is this, quote-unquote, the correct definition? It's kind of arbitrary. Doesn't really matter. At the end of the day, what does matter is that when we put in our numbers, whatever answer we get needs to match this. So F2 here was 0.12, that's negative. Plus 0.1228873, I get a positive 0.002873, and by the definition I just gave you that positive is out of the page, this is positive. What does that mean? It's out of the page. Boom, that's the direction of my net force. If it was negative, that'd be into the page. Why? Because that's how I define positives and negatives in this problem. Positive and negative is all arbitrary. Which way is up? That depends on which way your head's pointed. You know, if I turn my head sideways, up is now, that way. Direction is all arbitrary. As long as you're consistent in your notation and other people can understand it. Cool. All right. Now, what happens if my wire is not straight? Or my magnetic field is not uniform? There's two scenarios here, and we're going to practice both scenarios. My hope, my dream is that you all can look at these steps and say, wow, this kind of looks like how we did that Coulomb's law integral. Because it's very similar. It's the same process. It's the process of doing any integral with vectors. So first step, draw a picture. Pick a couple small pieces of the wire to determine the direction of the force. Have a sense of what's going on, just like we did last time. When we did Coulomb's law, when we did the electric field. We picked a small piece of charge and we find the direction of the field. Then we write an integral. The integral we're going to solve. In this case, we want the force. So I get the tiny piece of force. That's equal to the integral of I, B, dl, sine theta. Then we write DL in terms of spatial coordinates. If my wire is left-right, I'm going to use DX. If it's up-down, DY. If it's in and out of the page, maybe DZ. If it's an arc, change DL to RD theta. Hopefully this is sounding familiar. Break into components if you have to. Generally, we're blessed that only one component will survive. Make everything in terms of spatial coordinates and integrate. Set up your bounds correctly as well. I noticed that was a really common mistake on the exam. Make sure you know what you're integrating over. All right, let's do it. We're going to do the easy case first, which is a straight wire in a non-uniform field. It's going to maybe seem complicated. Just trust me. It's a bunch of small steps that you all are very capable of doing. You're going to see what I mean. This, in my opinion, is easier. A straight wire carries a current of 3 amps in the positive x direction. It's a magnetic field given by B equals negative 5x squared y. This y is y hat. I just didn't. Y hat's kind of a pain to write notation-wise, so I made it capital. Anytime y'all see a bold letter like this is the unit vector, which means it points in the y direction. If it's positive, it points up. If it's negative, it points down. What's the direction and magnitude of the force in the wire between some point x equals 0 and x equals 2 centimeters? What if the wire was instead at a 30-degree angle? One step at a time. First step, draw a picture. On your picture, I want you to draw the direction of the current, and I want you to draw the direction of the field. And I'll get you all started. The current's to the right, so that's pretty easy. Just make a straight line to the right. I say it's easy. I'm struggling to make a straight line. Boom, there's my wire. We only care about a point 0 centimeter, and actually I'm going to write it in meters because, and 0.20 meters. I only need you to draw the field in between those 2 points because that's the only place I asked you to find the force. So great, there's my wire. I want you all to draw the field between those 2 points. Make sure your arrows are both in the correct direction. Make sure you draw a bunch of arrows. And make sure the size of the arrows corresponds to the strength of the field. This is kind of a good exercise in this. Try it out. If you don't know the direction of the field between these wires, good luck finding the force. Yeah, typo here. This isn't 20 centimeters, it's points. Yeah. Good catch. This should be 0.02. In my head, I was thinking 20 centimeters.
I'm sorry. I didn't know that they do that.
That's fine. You can call it as a big. Yeah, it's actually fine. This is important. I didn't clarify this. We're going to call y in the up-down direction. Y is going to be up-down, just so we all get the same answer. If you decide to make y into and out of the page, it'd be fine. You would just have to clarify that. We're going to call y up-down. You wouldn't have been wrong. There's no rule that says y is up and down. That's why generally I
No, it's the x. Yes.
I would have given you with that new, yeah, which way is the better? What's the value of the field? What happens on the other side? Yeah. They're very easy. So your arrows, as you draw these arrows, are not to the side.
We're assuming it's negative y hat, so it's pointing in the negative
All right. How do we find the direction of the field? How do we draw it? You just pick some x values and start plugging them in. What's the value of my field at x equals 0? 0. Negative 5 times 0 is 0. Great. Now if I plug in a number that's slightly bigger than 0, which way will it point, up or down? Will I get a positive number or a negative number? I'm going to get a negative number. I get a tiny little arrow here. If I move a little bit to the right, as my x value increases, what's going to happen to my field? Bigger or smaller? So as x increases, I have the squared term. So it should be getting bigger. X squared, as I get closer and closer, it gets bigger and bigger and bigger and bigger. It's following this x squared distribution. All right, this is fairly important for us because we need to find the force on this. So the next step, find the force. Pick 2 different spots on the wire. I don't care what spots you pick. Generally, we use symmetry. In this case, it doesn't really matter. Pick 2 different spots. Find the force on a little spot here on the left side. Find the force on the spot over here. Find the directions of those forces. Notice I didn't make them arrows. You need to make them arrows. Look, great. There's 2 arrows. Find the direction of the force on each of those. You need to know what the force looks like across this wire. How do you do that? Sample. Pick a couple random spots, just like I did.
I think I read it wrong. You're not asking for the full force across that section, are you?
Yeah, full force.
Oh, really? You know if this is right?
I do not remember. You lost a 3. Oh, no, you got the 3 there.
Yeah, I just didn't plug in the
Yeah, the 3's cancel.
Yep.
Which is convenient. Yep, that's it. It's super, like, it's really not bad.
Straightforward.
Yeah, it's really straightforward.
You were to say from playing.
What's cool is what we can just do is we can just turn our head and say my x-axis is now lined up with the wires angle. And why do we do that? At the end of the day, we're integrating over a straight line. But what's going to change in my equation?
You need to add both sides of the equation.
No,
That's what I thought.
the integration, we're integrating over I dLd sine theta.
Oh, okay. So it should be
The angle is the only thing that changes. Yep.
For the part B, did you just take the final answer by sine 60?
Yeah. That's the whole point. All right. Okay. So which way is the force on these? Again, you point your fingers, direction of it. The force of this one is into the page. Force of this one into the page. If I just pick 2 random spots and they both have to be into the page, well, again, if the magnetic field's always pointed down and the current's always pointed to the right, everywhere on the wire is going to have the same direction of force. That's very important because what does an integral do? It adds things. I need to make sure I'm adding correctly. If they're all the same direction, great. Add them all up, done. I don't even have to worry about components. They all point in the same direction. We are going to very quickly learn when we solve this problem, which should look a little familiar. This one, they don't all point in the same direction. You have to break into components for this one. It's fine. It seems bad, but it's really not too bad. All right, next step. Build the integral. F equals the integral of I dl times b times sine of theta. Go ahead and do it, y'all. Like this. So theta here is the angle between the current and the magnetic field. I is I. B is the equation I gave you. And change dl to the direction that the wire is moving. It's a straight line. Call it whatever you want. It's actually worse than I thought for this one. Because if you do orient it upwards,
Oh, it's not just this?
you're no longer integrating. Your x is not 0.
I didn't think about that.
I didn't think about it either. That's fine.
It's still doable, right?
It's still very doable.
Yeah.
Oh, no, that's fine. I just said what's the force between some point x equals 0 and x equals 2 centimeters. I'm still going to fix it. X equals 0, it's just a longer piece of wire.
Okay.
No, but it is kind of messy. I think I'm just going to skip that one.
Okay.
Yeah, it's not what I wanted.
Yeah, because you are talking about that whole length, right?
Yeah.
The way it's worded, I thought it was just like a point between those points at some point.
Part B is not what I wanted.
Yeah.
Part B.
So you can't just do the sine of 60 on top of the answer, right? Because of the variance?
No, because I'm integrating. If I'm integrating over the length of that thing, my dimension there isn't 0 to 0.
Right.
It's not dx anymore. It's some new dimension, and I would have to get that x equals.
Change of coordinates.
Yeah. It's not the worst thing, but it's just I don't want to overwhelm.
Yeah, definitely not.
Yeah, what's up?
Leader, bro.
I would just yeah, don't do B. I originally intended would be simpler. For B, I was hoping the way I originally was thinking this was not actually correct. The more I think about it, was just like, oh, you just changed sine of theta to sine of 60. But it doesn't actually work out that way because your x value. Anywho, I'll chat about it after we solve this one. Don't worry about B. Don't worry about B. It ended up being more not crazy complicated, but more than I wanted. I don't want to scare you all off. All right. So hopefully, though, you are cool with this integral. The integral of what's I? It's 3. Oh, something very important. These are absolute values. Make sure you put absolute values. Why? Direction comes from the picture, not from the math. Change that to dx. Change this to 5x squared. What's my angle? My angle here is 90. And my bounds of this integral are from 0 to 0.02. This should be a very easy integral for you all to solve. It's the integral of 5x squared. It's just the integral of x squared. What's the integral of x squared? X cubed over 3. Look, we even have a 3 in front. It's so nice. So this integral is just 5x cubed. Evaluated from 0 to 0.02. That's it. Super easy. This straight wire with the non-uniform magnetic field should be a very easy problem for you all to solve. And so you get 4e to the minus 5 newtons. Now, I want the direction. It says magnitude and direction. That's going to be a really common trend on these problems. And this is into the page. Not because of the math, but because of the picture. We relegated the direction to the picture. If you wanted to find the direction from the math, you'd have to do a cross product the official way. All right, that's it. Now, my dream here was for the angle that was 30 degrees, just to kind of walk you all through this part B and why we're not going to do it. My goal is to give you all this problem. Hey, here's a wire going up at an angle. This angle is 30 degrees. My magnetic field is still pointed down. Find the force in that wire. Between x equals 0.02. So I'd have to rephrase the wording to not between some point x equal, well, even then it wouldn't spare you. If you want to find the force on this, you'd have to basically make a triangle, because I say find the force between x equals 0 and 0.02. This coordinate, you'd have to kind of find the length of this rod, the length of this wire would no longer, your bound to your integral would not be 0 to 0.02, or if it was, you'd have to you'd have to change this dl to dr, and then you'd have to get dr in terms of x. How would you get dr in terms of x? A triangle. So r equals x over y. So if I wanted some length r, so my bounds of the integral would be dr. dr equals square root of x squared. R equals x squared plus y squared. And it's just worse than I want it to be. Long story short, don't worry about part B. That's beyond what I want y'all to do. It's not terrible, but it's beyond what I want you to do. Great problem for a physics major. The rest of you, don't worry about it. All right. This is the last problem we're going to solve today, and then we're going to call it kind of good. I don't know why I say that. The next two are really quick. We're going to do this, and then it's 2 clicker questions. And then we're done. All right. This one, I even drew the picture for you. How kind of me. In the image below, a uniform magnetic field is pointed into the page, and there's a current I traveling counterclockwise along a half circle with radius r. And then there's some straight wires on the ends. What is the direction and magnitude of the force on the half loop? Just focus on that for now. Just worry about the half loop. What you need to do is draw a couple pieces of current. Draw a couple pieces of current on this half loop. Find the direction of the force. And then, try to set up the integral. I believe in you all. Mathematically, this problem comes out very simply, but can you set it up? We're just focusing on the half loop right now. It's that easy.
And then you don't even need to integrate for just the constant one.
Yep. And the whole point here is remembering. I need to break it into pieces for them. Find on the half loop, find on the 2 straight pieces. What's it all together?
So it'd be twice this for the 2 sections, right?
Yep.
And then you can just add those.
Yep.
Okay.
Yep.
The important thing is
So yeah, draw a couple pieces. Find the force on those couple of pieces. If your picture's bad, the rest will be bad.
No, they don't give you a sequence. Your finger is the force, so they'll give you the direction of the field.
Is the direction still up for the
Yeah. And again, what's really cool here, and you see this answer. The length of this is just 2 times r.
Right.
So if you imagine straight that's right here.
Yeah.
The force on it's just I times the length of the wire times b, which is exactly what you referred.
I think I did that earlier.
But it's the opposite direction.
Yeah, like you integrate times 0.
It's a really cool trick. I'll mention it. I won't have it in writing.
Okay.
All right. So let's do this. So what's the direction of the force on this little tiny piece in the bottom left? It's going down to the right. So you put your hand down to the right and you swing it towards B, which is the inside. So what's the direction of that force? It's going to be up to the right. Up to the right. That's my DF1. We pick 2 pieces of the wire. We sample. How do you understand what's going on? You sample pieces of it. And that's my DF2. One's up to the right, one's up to the left. So what does this reveal to us? When we solve this problem, what's going to happen to our x component of the force? It's going to cancel, but our y component won't. What's also very important here is you see I do care about components. This one you got to split into components. You can see it from the picture. I've got vectors that aren't perfectly aligned. I cannot just build the integral like the last one, solve it, and call it done. I have to split it into components. If you do not split it into components, you're neglecting the fact that these vectors are not parallel and anti-parallel. So go ahead and build the integral. I'll start, f equals the integral of I dl times magnitude of b times sine of the angle between it. Build the integral, then break it into its components, x and y, realizing that the x component will cancel and the y component won't. The y components will add up, and then solve. It's all in variable form too, so you don't actually... And the integral is very easy to solve. This is a very easy integral. If y'all can't solve this integral, no idea how you passed Calc 1. Building it's the hard part. Building it's the new skill.
Would this still be negative?
Yeah.
And like vector form?
So that's why these positives and negatives are all just kind of arbitrary.
Yeah. Because if
the reason here,
yeah.
what's cosine of pi?
-1. Okay.
Yeah.
So it doesn't you can still write it like this for the total net force, or no?
They should add.
They should
When we're
add,
adding
that's
them,
something, yeah.
you find the direction based on the picture.
Right.
We haven't actually.
Oh, okay. That's what you're saying. Because it would be going up. They're both in the positive.
Everything's
Y.
going up.
Okay,
Yep.
gotcha. Thank you. I'll put a J hat.
All right. So what am I going to change? Look, I is I. That's easy. What am I going to change DL to? What's my rule say? If I have an arc of wire, how do I break it into? How do I change DL to something useful? R d theta. B is B. It's just given as B. Awesome. Sine of the angle. What's the angle between my vector here and the magnetic field? And this one might be a little tricky to see. It's 90 degrees. One's into the page, one's flat on the paper. If it's flat on the paper, I don't care what direction it is. Look, I'm just going to draw a bunch of random vectors. Here's a bunch of vectors. What do they all have in common? They are all perpendicular to a vector pointed into the page. They all swing 90 degrees. I don't care if it's flat in a paper, that's 90 degrees to into the page or out of the page. So what's this angle? 90. So that's just going to be 1. Great. Do not integrate this yet. If you integrate this right now, you skipped a step. Remember, integrating is addition. That's what you're doing. I'm adding these forces together. Am I allowed to just add these 2 arrows together? No. What do I need to do? Components. We're not doing something new here. It's just in a new way of writing it. So, break it into components. In the x direction, you all need to find this x component of the force. We're blessed that it does kind of work out the way you want it to. What do you all think we're going to multiply this by to get the x component? It is going to be cosine. We're kind of blessed that it works out that nicely. If you're like, how is it cosine? Take one of these forces. Take this little arrow here. If I want to break this into its x component, I'm going to draw this little arrow. This little angle here. What is very, very, very convenient here is this angle is the same as this angle. I know these colors aren't very easy to see. Maybe if I use black. If I want to break this into component, I'm going to use this angle. This is the same as this angle. That's the angle I'm integrating over. It's very convenient that the angle I'm integrating over, because I'm integrating from this spot here, this current here, all the way to this current here. I'm sweeping along the path. Anywho, we're blessed that it turns out to be what you want it to be without much thought. So I times r times d theta times b times 1 times cosine of theta. But again, we actually know through symmetry, what's this going to be? Because technically this integral is not quite set up, like, it's fine. The x component's 0. Go ahead and do the y component, though. Do the same thing. Hopefully you can guess what you're going to do for y component. I have not put the bounds of the integral here, but I did tell you all how to figure it out. We're integrating over theta, and theta here is going from this flat line here all the way to this flat line over here. I'm sweeping over half a circle. What should be my beginning angle? What should be my final angle? If you're using degrees, you're doing it wrong. Actually, degrees will work out fine, but you generally don't use degrees for integration. Degrees are made up. In this problem, it matters, but in general, 0 to pi is better. Okay, it's better to use radians because if you're integrating over theta, say it was just d theta, then it turns into theta, and you do care about using pi, because radians are like a real thing from the real world. 180 degrees is we made up.
Yeah.
Yeah, I know.
Alright, hopefully y'all realize it's from 0 to pi. That's half a circle. And if you put 0 to 180, it will technically work, but that's not a good, you need to work in radians. Radians are real. Degrees are made up. You're like, what do you mean they're made up? Radians are defined by the circumference of a circle, literally from physical measurements of reality. 360 degrees for a circle is made up because humans decided that was a nice angle to use. Anywho. Ends up really easy. I times r times b times the integral of sine theta d theta. This is where I told you, if you cannot integrate this, I do not know what happened. You might have forgotten things. Look, we forget things. Life happens. But hopefully you know that this is negative. You maybe forgot the negative sign. And we get that this is 2I times r times b. I am going to now show you all a little trick to solve this. Do I recommend this trick? If you understand why, it's a very useful trick. If you don't understand why, do this technique. All right. There's a really cool trick to this that some of you, when I've gone around, have touched on. So back when we solved this problem, in fact, actually, I'm not going to mention this trick actually until we solve the next two problems because they're going to help us answer it. They're going to help us understand why this trick works. Real quick, this says, what's the direction, the magnitude, the force of the two horizontal pieces of wire? That's very easy. Both of these pieces of wire are also going to experience a force upwards. What is the force on a straight piece of wire? I times L times B. Each of these wires are length L over 2. So I'm just going to quickly kind of write this out and move on with our lives. So I'm going to steal this picture. If you all want to find the force on these, we've already practiced this a little bit, so that's why I'm kind of going to go through it quickly. That's L over 2, that's L over 2. If I want the force on a piece of wire, it is I times L times B times sine of theta. So if I call this wire 1, call this wire 2, the force of 1 is I times L over 2 times B. The angle between them is, both of them is 90. Great. That's the force of 1. Which way is it? Up. Right hand rule, y'all can practice that for yourself. Force. Force. F2 is the exact same thing. That one's also up. If I want the net force in the entire wire, if I have 3 forces and they all point up, what can I do with the forces? Add them up. So F of arc plus F1 plus F2 just equals 2 times I times R times B plus, hopefully y'all can see L over 2 plus L over 2 is just going to be L. I want to save myself a little bit of writing. Yay! That's the answer. That's the total force. So what was the purpose of this problem? 1, to realize how to do an arc. 2, to realize if I got 3 wires, find the force on each and add them up. Great. All right, 2 clicker questions, then I show you the trick, then we're done. What's the direction of the force in the bottom of the loop? Shown below. Yeah, that's good. We'll just do this. Oh my gosh, the last clicker's been open for 55 minutes. All right, great. That's more than enough, and didn't even realize. That's all right. Some people didn't get it. Sometimes things happen. All right, I'm going to give you all 30 seconds for this, because either, what's the direction of the force in the bottom of the loop shown below? 30 seconds. Make me proud.
Oh, yeah.
All right, 5 seconds left. Make sure you answer. 5, 4, 3, 2, 1. Great job, everyone. We all remembered that if the angle between them is 0, the force, now almost everyone. They're aligned on the bottom of the loop. The magnetic field's to the right, the current's to the right. What's the angle between them? 0. What's the force? You know, we're so close. It's all right. That's pretty good. There's the field. There's the current. They're in the same direction. Hey, if the force on the bottom is 0, what's the force on the top? 0. Also 0. Fantastic. All right, let's look at the other sides. These are really cool problems when they come together. You're going to see what I mean. What's the direction of the force for the right side of the loop? Same thing, we're going to go quick. Give y'all 20 more seconds.
Oh, yeah, no, it went. I think even when we tried to explain I was like, okay, sure.
That's good. It's fun to give them a little bit tighter, I guess. Look at all that enthusiasm. Yeah. All right, 10 seconds.
Is this going to do a segment before?
Yeah, we're not actually going to solve torque.
Like at all, or just today?
No, all just for the sake of time. I should say
I think you rushed over it.
Yeah. All right, 5, 4, 3, 2, 1. Remember, something that's really helpful is it's really helpful to draw the field where the thing is. So there's my current. There's my field. Put my finger on it. Swing it towards B. The force is into the page. If this side is into the page, that's the answer. Into the page. If the right side, the current's up and it's into the page, what's the direction of the force on the other side? What's going to happen to this object? If one side's getting pushed in and one side's getting pushed out, it's going to spin. It's going to rotate. Ta-da! This is electric motors. This is how electric motors work. This basic principle right here. Every single piece of equipment that you all own, that when you put electricity into it and it makes something move, this is how it's happening. Every single piece of equipment, this is how it operates as far as taking electrical energy and converting it into motion. Now, so that's real quick. You know, this is called torque and a current. We're not going to actually calculate this. We'll talk about this more. Real quick, though, what I want to point out is the net force is 0. So really interestingly, it spins, but the net force is 0. Why is this useful? This is the trick to this problem. I am not actually going to write this in writing because I think if people don't understand why, they're going to end up making too many mistakes with it. We're going to do something kind of interesting here. And this is going to be very quick, and it's going to make your life so much easier if you understand the trick. If not, go through the other process. There's a really cool trick, which is that the rule is that the force on a loop of wire is always 0 due to a magnetic field. Always. Why? On one side, the force will be one way. On the other side, the force will be the other way because the currents will be opposite directions. Why is this useful? If we made up a loop here, if we made up a loop of wire such that it was doing this half moon shape, here's the really fun fact. If you find the force on this top piece, it is exactly equal and opposite to the force on this bottom piece. It's a really cool trick, and let me just do that real quick for you all. What is the force on this top piece? It is a straight wire. So it's ILB sine theta. What is the length of this wire? It's 2 times R. The magnetic field is B. The angle is 90. Oh, look, it's the answer we got by doing an integral. This is a really nifty trick that you can do if you remember that the force in a loop is 0. If you just close the loop, find the force in that straight piece of wire, you're done. The integral is maybe the safer bet. I don't know. Both are good. This one, you just have to understand that the force of the loop is 0. This one, you have to have a better conceptual understanding, which is not always easy. Conceptual understanding is actually harder than the math, in my opinion. All right, y'all are free to go. Have a good one. Nice work, y'all. I know we didn't take a break, but we got out an hour early, so trade-offs, right?
Yeah.